the beginning of the end. The tears, they shall flow. The comfort, it will come. Kleenexes are here. I can't resist. It's end of Calc 3. I have to give some monologue, the nature of this, the wonderful journey we've taken. It's now sadly coming to an end. I know you'll miss me, but you need to move on. The grass is not always greener, yet still we must try to make the journey. Unless you all want to fail and come back here and just take it again and again. And you can do that, but we always strive for forward progress. This is not a line integral on a conservative vector field that creates a complete simple closed curve. We want work to be done. We want Green's theorem to apply. Your education has come full circle in a non-conservative way. Boom. Let's just end it right there. Because we're doing this. Seriously though, we're doing the rest of the material for Calc 3 in one go because it flows very smoothly. I don't want to break it up into 4 sections, frankly, because I don't have a lot of time, and it honestly doesn't need to be. So how this stuff flows, I'm going to show you. Where this stuff comes from, I'll talk about it. We're going to talk about a lot of different things in this section, this large chunk of material. What we're going to talk about is a flow from what surface integrals are, how they relate to surface area, how we can parameterize surfaces so that we can find surface area easier and do work on a vector field along surfaces, not just along curves. How we can use divergence theorem to our advantage, what that even means, and then finally what Stokes' theorem is. Stokes' theorem is a generalization of Green's theorem, and we'll talk about how they relate. You'll see how they relate. I want to get into the start of it. We're going to relate it back to that. You've seen that. We've worked on that for over a chapter now. What a double integral does. It says, I want you to look at a region. I want you to look at a region, but that region has to be on a what? Plane. It's got to be on a plane. In other words, R is a flat region. That's how double integrals work. They're a flat region. Now, what do double integrals do? Well, they either give you the volume under the surface over that flat region, or if F is the mass density function of that little plate, that really thin plate. Remember that? The really thin plate sitting on a plate, like super flat, like that doesn't have any real width to it. If F is the mass density function, it's giving us the mass of that plate that occupies the region R on a flat plane. So if you feel okay with that one. Okay, that's what a double integral represents for us. Now, imagine this. What if R is not flat? Well, if R is not flat, can it possibly sit on a plane? If R is not flat, can it sit on a plane? No. Then R is no longer flat. That means R is no longer a plane. R is now a surface. This is what we're going to be considering. What if the R that we have, it's still really thin, but it's no longer flat? It's a surface. That's what a surface integral starts to describe. How to do double integrals over a surface. And we'll talk exactly about what that means. So if R is still thin but not flat, then our region is actually a surface. This is going to lead us into what surface integrals are. We'll talk about what they are. We'll talk about what they mean. We'll talk about the formulas, what these mean. I'm going to say, hey, we're going to jump back and do 4.5. It's literally a one-sentence lesson for section 4.5. It's why we skipped it. If you're like, man, we went 14, 1, 2, 3, 4, 6. Leonard forgot how to count. I forget how to count. We skipped a section. Why? Because it's literally right here. And I will show that. I'll prove it to you. So firstly, though, we got these these integrals now, these double integrals over these regions that are still really thin, but they're not flat. That means they're over a surface. This is a surface integral. So a surface integral, it's a double integral over some really thin plate that's not flat, a surface. And some function. What are we going to let that function represent? What do you think? I want to make you consider the comparison here. This is a double integral over a mass density function where this region has some area, and we integrate across the area of that region. Does that make sense? Okay, this is the same thing. This is a double integral where we have a mass density function over some region that's a surface. We don't just have area anymore, we have surface area. Does that make sense? It's not a flat concept. You can't integrate across a flat concept anymore. It's a surface area concept. So not just area, but surface area. Not a flat region, but a curved region, something that has a surface to it. Now we'll make one more stage. You guys okay? Are you guys okay with that one? That this is a surface area concept. Not just area, surface area. One more statement. Imagine this. Imagine that we have this not flat plate. So this surface. And I take the surface. Are you looking up here? Look up here. I take the surface and I look straight down on top of it. Is it going to look flat? Straight down on top of it. In fact, that look that it has to it, that flat look, is a projection onto the XY plane, or the YZ plane, or the XZ plane. But it could be a projection onto a plane. Does that make sense? That projection, this should be sounding kind of familiar to you. The projection of the surface is our region. The projection of that surface onto a plane, that gives us this R that you see here. So the projection of the surface onto a plane is giving us R. So here's like maybe a 15-second recap about what this stuff is. We'll run through the formulas that you need to know what they mean. I'll explain them to you. And then we'll do an example very, very quickly to get our feet wet. Again, I think I said this before the opener, but basically you're going to have idea, one example, we have to move on. Idea, one example, we have to move on. We're not going to get a whole bunch of examples here because, frankly, they're very, very similar to each other, and I don't want to waste our time. I'd rather go on with kind of more of the theory, the lesson part of it, than just crush examples. We've done a lot of that. Mostly here at this point, since you guys are, really mathematically mature after doing all this stuff, all right? You know how double integrals work. You know how triple integrals work. You know how all this stuff works. We're just dealing with the theory behind it now. How can we use it to our advantage to make our lives easier? Not harder, but do different things with it to make our lives easier. Do you guys get that? So I'm not going to try to give you really hard examples here. What I'm trying to do is to get you to understand the concept, to truly understand it. Because if you get it, then you can practice the easy examples and you can do everything on your own. Does that make sense? If you understand it, that's my job as a teacher, to make sure you get it. You actually understand the concept. The concept here is we used to have double integrals where a region was flat. And we used to have this thing that gave us a mass density at every point along that flat region. Does that make sense? A really thin little plate. And now we're saying, imagine that plate is no longer flat. That plate is now a surface. It's still really thin. And this is still the mass density function at any point along that surface, around that surface. That works. Look, surface. 3 three variables. It's creating that mass density at every single point on that surface rather than on the flat plane. Do you guys see the difference in it already? We go, okay, well, can we still do it? Yes, we can still do it. In fact, if we look down on the top of that surface, it's going to give us a region on a coordinate plane. We can structure our surface integral. So surface integral means basically just finding the mass. If I do this, finding the mass of a really thin plate that has a surface to it. Does that make sense? And we can do it like this. Now, what in the world is all this stuff coming from? Here's section 14.5 in a one-sentence statement. Are you ready for it? Here it is. If you eliminate this, and you treat your function in terms of x and y, so z is a function of x and y, or y is a function of x and z, or x is a function of y and z, or you treat one variable as dependent on the other two, then this right here, and this right here, and this right here are the exact thing that you see in section 14.5 for surface area of that function over that region. It's the exact same thing. That was a one-sentence statement. If you read it back, that was one sentence. I use a lot of ands and buts, but still, that was one sentence. That's 14.5. So watch. Are you ready for it? 14.5 just has this. That's it. Now, let's look at it. Let's look at what this does. What does F give us in this context? What is that? Mass density. What's this piece? Surface area. It's giving us the mass density at every point on the surface with respect to area. It's just finding the mass and adding it all up. That's literally it. That's what section 14.5 did for us. And now we say, suppose that we also want to find the mass at every point along that surface with respect to its surface area. Boom. That's now this section. That's what surface integrals start to do for us. Do you guys see it? It's kind of cool, right? I'll say it to you another way. Suppose that the mass density at every point was constant and had a value of 1. 1. Do you remember talking about that? You'd have surface area and surface area. And if your mass density was just constant 1 every single time. Remember talking about how we can use 1 and get different things for it? So if you had a double integral of 1, actually just give us area instead of a mass, or it's giving us like triple integral of 1, give us volume instead of mass. We can say 1 for mass density and get surface area instead of mass. That's interesting. Cool, right? So I hope I made the case for you that the reason why we didn't cover surface area explicitly is because it's literally covered right now. And if you don't believe me, go back and look at it and say, oh my gosh, he's right. If you just cover this up, you have these 3 formulas for surface area. And if you just treat the mass as constant 1 at every point, you literally just get the surface area of the region that you're trying to define. That's what surface integrals do anyway. They take the surface area times the mass and get the mass density and get the mass of the surface, the really thin plate. Show of hands if you're okay with that one. So that's it. So this encompasses surface area for us, and you're going to see it a little bit later. A couple points I want you to look at. The reason why you have 3 formulas is the same reason why you had 3 different options for triple integrals. You could choose to do z simple, or y simple, or x simple first. You guys remember doing that with triple integrals? Well, you can choose to define your surface. Look, your surface would be 1 variable equal to 2 other independent. Does that make sense to you? 3 total variables, 2 are independent, 1 is dependent. You can choose to define it in terms of x and y, or x and z, or y and z. I just want you to look how it works. If you define z as x and y, then you'd have an x and you'd have a y, but you wouldn't have a z. You'd have a function that's redefined in terms of x and y. Does that make sense? Then, oh my gosh, what are these things? Well, this is the function that you just defined. You couldn't take a partial derivative with respect to z here. There are no more z's. But you could take one with respect to x and one with respect to y. And that's what that's doing. Here, you could take one with respect to x and z. Here, with respect to y and z. And so it's just kind of the same formula. It just depends on what you want to define your surface as. Whether you want z equals, think like z simple. Y equals, think like y simple, or x equals, think like x simple. Does that make sense to you? So that's the idea. I'm going to show you one example real quick, but I really want to know if this makes sense to you. The idea of flat versus non-flat area versus surface area, how you literally do surface area with a projection over R times mass density. That's what it is. It's surface area over this. This is surface area of that function, where R is the projection of that function onto the xy plane, or the xz plane, or the yz plane. That's what that is. Now it just says, take that stuff, multiply by the mass density at every single point, and add it up like every integral does. It's just an infinite sum. It just adds up the mass densities of all the points, gives you the mass of the surface where the projection is R onto a coordinate plane. Is that well explained for you guys? I want to make sure that it is. Are you sure? Okay, now the important question, how do you do it? It's honestly not that hard. It really isn't. The most important thing you can do is define your function in terms of x or y and z and follow the correct formula. If you do z equals, then all your stuff better be in x's and y's. If you do x or y equals, all your stuff better be in x's and z's and so forth. So let's do one example. I'm going to have to erase this, so are there any questions on what this stuff means? Okay. Oops. Let's check out the look at this thing first. Let's check out the look at it of it. What is this thing? What is that? Is that the surface?
No.
What is it?
Mass density.
Mass density. That's the mass density function. It gives a mass density at every point on our surface. So just like on double integrals, I can't just give you this and say, do it. I got to give you this, and then I got to give you a surface that you're integrating over that has a surface area. Does that make sense to you? You got to have that. So I'm going to give you the surface. So where S is a plane inside a cylinder. Okay, so we got this double integral, but it's no longer over flat region, it's over a surface region. It has surface area. We have a mass density function every point on that surface, and I'm giving you a surface. Notice, this is not flat according to a coordinate plane. It's not flat, it's going through 3 space, all right? Yes, it is a plane, but not according to a coordinate plane is it considered flat. Does that make sense to you? So we go, okay, well, what's the most important thing we can do? The most important thing we can do is, like I said before, define a function for your surface. Look very carefully, please. Do not lose this. Do not miss this. This surface, it ain't coming from here. This is not your surface. This stuff, it ain't coming from the function inside your double integral. This stuff is coming from the surface that I'm giving you. It's coming from this. This is what gives you this and this and this and lets you redefine that. Does that make sense? It's all based on the surface stuff. This is just going to get redefined. It kind of plays along. It's second fiddle. So this is going to stay, well, some of this stuff is going to stay. We're going to redefine one of the variables depending on whether we want to pick z equals or y equals or x equals, but that all comes from the surface definition. So we're going to look at that. What would the easiest variable be to solve for? Just like, it's not z simple because we're not doing triple integral, but kind of like that, or x simple because we're not doing triple integral, but kind of like that. Let's look at the variables that would be easiest to solve for. Let's knock one just right off the table. Y. I would not want to solve for y. Why? Because I have 2 functions that both have y's in them. That'd be pretty hard to do if I'm trying to get one function. Does that make sense? Because I have y equals something and y equals something, and it wouldn't be the same something. That'd be hard. I could do x. I could solve for x over here, but that's kind of funky too because I have a square root and it doesn't have a z, and so I wouldn't be able to solve for that z. I'd need to encompass my other variables with that. Does that make sense? So I'm going to look at this and go, well, I could solve for z. Now, it doesn't have an x, but x is wrapped up in a cylinder. So this is cylinder, this is plane cutting through the cylinder. In this case, because I don't want to solve for x, I really can't solve for y. It leaves me with the only option, I've got to solve one of these functions for z. That will become my function. Head nod if you're okay with that one. So we'd say, let's let z equal a function in terms of x and y. It doesn't have to have both x's and y's, but you can't have two different functions. That's why we didn't pick y. We can't have two different functions out of this thing. You have to have one function. So in this case, we'd say, hey, z equals 4 minus y. Pretty easy. Wonder if that makes sense to you. Yeah or no? Okay. So we've said no, yes. Here's how this stuff works. Please look carefully. I don't want you to lose it. Again, you know how double integrals work. It's just the setup. The whole class has been set up. Past like the first two chapters. It says, well, let's start redefining it. Let's look at our region. We'll do that later. All about setup first, then look at the region. Let's look at the function, the mass density function. Could you redefine this so that you have only x's and y's, and if you have any z's, you change them into x's and y's? Could you do that? Now that you've defined this thing in terms of x's and y's, the answer is yes. So let's start doing that. So using formula number 1, write your double integral. Literally, write your R. Don't skip that step. I told you that last class. Do not skip that step. You'll deal with your region later, but get your setup correct. Hey, according to this stuff, do I want x's? Are x's okay?
Yes.
Are y's okay?
Yes.
Are z's okay? No. So what's our z become? If you can make that jump, you're halfway there. Are you guys okay with where that comes from? You need to define one of your variables in terms of the other two because we don't have a triple integral. We have a double. That means only two variables. So you got to pick one. You can't have x's, y's, and z's because you're only integrating 2 times. You got to integrate 2 times, you get 2 variables. That's why we did that. So this is our mass density function as redefined using the surface that we're going over. That's the idea. Head nod if you're okay with the idea. Now, the df. Okay, this stuff. That's the idea of surface. Hey, look at that. If ds is the idea of surface area, and that's the mass density function, we still have the mass density function. ds is surface area, right? This is surface area over that region, the projection of S onto a coordinate plane. No problem. That's just surface area, so we rewrite it. Okay, surface area. I know it's going to be a dA. Don't change that yet. We don't know if it's dx, dy. We don't know if it's polar, rd theta. We don't know what it is yet. So you leave it. Don't do that. Don't do anything until you've actually drawn the region. Are you listening to what I'm talking about? Please don't do anything with this yet because you don't know what's going to happen unless you draw the region first, which we're not going to do. Now, what this stuff means, it's kind of some different notation. We're going back in time a little bit. Do you remember what that g with a little x, the subscript, meant? Partial derivative of g, whatever you've defined with respect to x, and then with respect to y, the 2 variables that you just redefined your function as. So let's do that. So if this is, look, hey, if z's the function g, then we should be able to find from this partial derivative of g with respect to x. Hey, what's the partial derivative? This is g. Partial derivative of g with respect to x?
0.
Partial derivative of g with respect to y? Hard? You just gotta follow it. You just gotta know what it means. And if you know what it means, it's easy to follow. Just put that stuff in here. So okay, well, it looks like we have, tough one. 0 squared plus -1 squared. Is that it?
Plus 1.
You know some people are going to forget the plus 1, right? Don't forget the plus 1. That plus 1 matters. So fancy for art with that one. Okay, so let's clean it up just a little bit. Combine like terms, you know this from like basic calculus. Combine like terms before you do any integration at all, like ever. So here we have x plus y plus 4, and then we got this square root of 2 hanging on, dA. Okay, right there I'm going to do a little pause, okay? I want to make sure that this is totally understood by you about where all of this stuff comes from. Show of hands if you feel okay with it. Literally just formula, it's just surface area from before, which we didn't cover, but it's there, times mass density at each point. We make our transition by saying, let one of your variables equal the other two, become a dependent variable. It lets you parameterize according to those variables, lets you find partial derivatives really nicely, lets you do something kind of simple, and it leaves you with a chapter to go. It leaves you with, hey, if you ignore all of this stuff and just look here and say, well, that's a double integral. What's your region? Your region is the projection of this thing onto, okay, now you think back to this. If we let z equal something, it's very much like being z simple. What plane is this projection going to be on? Yes, that's why I said think like it's z simple. Because it's going to have your brain go, z simple means my r is on the xy plane. That's exactly what's happening. You're kind of cheating a triple integral here, okay? Kind of cheating a little bit. That's okay. We're just redefining in terms of two variables and using that. The projection will be on the plane that you redefined as. Does that make sense to you? This r should be on that plane. This r would be on this plane. This r would be on this plane. That's where it comes from. So because we picked z equals a function of x and y, our region, our r, is on the xy plane. Should look familiar. Right before this, for triple integrals, we just let z simple, and then we'd have r's on the xy plane. Draw it. Man, this stuff should be coming back to you. We always draw our region, like every time. Draw it. Just draw it. Okay, so well, what's going to happen? Is this, hey, can you put that on the, oh my gosh, look at that, how about that? Can you put that on the xy plane?
Yeah.
What is it?
Circle radius 1.
And it's literally on the xy plane. Getting kind of tired of that. Same thing. Oh, at least it's nice. Now, can you put this on the can you put this one, on the xy plane, or this, it doesn't matter. Can you put that on the xy plane? What's the value of z on the xy plane?
0.
So, x squared plus y squared equals 1. That gave us a circle. Z equals, I'd do it this way probably. Y plus z equals 4 on the xy plane means z equals 0, which means y equals 4. You go, wait a minute. Y equals 4, that's like way up here. That's y equals 4. That's what that is. Here's a weird question. Why don't they intersect? Think about what this is. What is this? Come on, people. What is that? Along what axis? It's going like this at you. What's this? Don't say a line. It's not coming from a line. It's a plane. It's intersecting the xy plane at a line, but it's a plane. It's a plane doing this. So you have a cylinder, you have a plane. It's slicing the cylinder, but not on that plane, not on the xy plane. It's just out here in space. So the surface we're talking about is the surface that's created when this plane slices through this cylinder and gives us this oblong shape right in the middle of, that's why it's not flat. Because it's not flat with any of the chord planes. It's coming through space like this. Yes, it's a flat surface, but it's not flat according to the plane. Does that make sense to you? That's what we're doing. That's what we're trying to find, well, the mass of that little disk. Sort of disk, stretched out disk. That's what we have here. Show of hands to understand the concept. That's pretty cool, right? That's what we're doing. That's why they don't intersect, though. They're intersecting in space. Does it bother us? No, we don't care. Because all that's happening when you look back at this, you are literally looking where this plane slices your cylinder, you're looking down at it and you're saying, hey, where that plane comes out, it's slicing the cylinder, that region, it's all contained within that cylinder. Do you guys see it? It doesn't matter that it's slicing above, this is still your region. That's still R. It's just a projection of your surface. If you're looking down, right down on top of it, it'd be what it creates on a coordinate plane. So if it's feel right with that one. That's your R. Now, you tell me, after all the calculus you've done, all the double integrals, how would you choose to define that? Now, what you watch carefully, okay, because this is very important for this stuff. As soon as you start doing polar, and you start saying this, and you start, please watch, as soon as you start saying, well, now r squared equals 1, as soon as you make that jump, look carefully, as soon as you make that jump, it doesn't have to be x and y, right? It could be x and z or y and z. As soon as you make that jump from now on, I want you to say, well, then define these two variables, because when you make that jump into r, x has to be either r cosine theta or r sine theta, depending on what axis you're choosing. We're going to choose r cosine theta, which means that y has to be the other one. What about z? I don't care about when you change to z. You'll just have x's and y's. So this is our new function in terms of polar, and now we make the jump. So we don't even talk about r until we get right down to here. And then go, hey, double integral, project the picture of your surface onto a coordinate plane. Then look at what you have. If it's a circle or that's pretty nice. Use polar. Can you please redefine this double integral in terms of the region you've now created? Keep in mind it's a full circle with a radius of 1. So let's see. Should you still have all of this stuff? Not if you did that. That's why we wrote this stuff out. Because you're not going to get a whole lot. You could get like x squared plus y squared in here, but you don't have to. If you get x's and y's, or in other ones, x's and z's, y's and z's, whatever, you'd have this redefined already if you did this. So as soon as we choose polar, you have that definition. So let's write that. Instead of x, I'd write r cosine theta. Plus, instead of y, I'm writing r sine theta. 4? Yeah. Square root of 2? Yes. Then what? And we know this already. This is old stuff. We always go r to r first, theta to theta last. We got to match these up with these things. R goes from 0 to 1. We're in our region right here. This is literally the region you create when you're looking down at your surface on top of a coordinate plane. And then we're going to go around for a full circle, 0 to 2 pi. That's it. After you understand the concept of how to change these really weird things we're creating into some double integrals you're used to, this stuff gets pretty easy. It's all about understanding how to go from here to here. After that, it's just double integrals. It's just some regions you're going to be really, really used to. Kind of saw it in Green's theorem, right? Makes double integral, pretty easy one. Deal with the region, you're done. Sometimes this stuff looks so overwhelming. When you look at it, you go, dude, these symbols look crazy. What's going on? But once you understand them, you go, oh, that's it? I'm just getting double integrals over a really easy region? That just made my life actually easier, not harder, easier. This is nice. Now, you work it out. Would you know how to work that out? What would you do? Don't forget the R, distribute the R, integrate with respect to R, do plug in 0 to 1, it's going to be kind of nice. Integrate with respect to theta, you got some sines and cosines in there. 0 to 2 pi, what you should get is 4 root 2 pi. Now, tell me what that number means. What is that? Say it louder. No, No, it's not surface. It would. Okay, now this is a good teaching moment for you. If this was 1, if that was 1, and that was 1, and that was 1, then this would have been surface area. Did you guys catch that? That's the whole point of the 14.5 thing. If that's 1, surface area. Did you guys get it? That's all that's happening. What is that? What is it? Come on, what is it? Mass density. What is this? Mass. Of what? That surface. Mass of that surface. A really thin plate. That's curved, perhaps. It's not, but really thin plate. That's what that mass, that's what that is. Is it making sense? Again, if that was 1, then yes, that would have been surface area of that plate. Show of hands for that one. Okay. That was the only example that I have for just basic surface integrals, because we're going to move on a little bit. What I want to talk about right now, we're going to get back to it, okay? We will, I promise. But I want to show you a different way. But in order to show you this different way, I have to show you how to parameterize surfaces. What that means is treat a surface like a vector function. I got to show you how to do that. It's not necessarily, it can be super hard, but I'm going to show you 2 techniques on how to do it that are very, very fast. Are you guys ready for it? You're not ready for it. Well, get ready for it. So are you okay on surface integrals for right now? I'm going to leave this on the board the entire time because I'm going to come back to it. I want to make the connection with what we're going to be doing, what we've already done, that we don't lose this. This is not like 7 different concepts. Okay, it's the same kind of the same concept over and over again until we get to divergence theorem, and then we start talking about surface integrals through vector fields, and then we start talking about divergence theorem, and then we start talking about curves through 3-dimensional vector fields, and that's Stokes theorem. We start talking about that. Okay. So you can kind of title this little subsection, just title it Parametric Surfaces. We're going to do quick examples here to get the concept. So here we go. This is all going to look like gobbledygook at first. I'm going to make it make sense with a couple examples. Just write this down. This is like the background behind how you do parametric surfaces. So if you've got this function of x and y and z, and you can redefine x in terms of a function where x is defined in u's and v's, and y, where y can be a function defined in u's and v's, and z, where z is a function in terms of u's and v's. If you can do that, and if vector functions are always the x thing I plus the y thing, we're calling it thing j, plus the z component k, then you can redefine a surface in terms of a vector function. Why? Why would you want to do that? Well, let's look at it. Verify that this would have 3 variables. Verify that this has essentially 2 variables. You eliminate a variable. Now, you listen carefully right now. Do you recognize that is exactly what we've done over here? It's a different way to do basically the same thing, just a slightly different way. So we're going to deal with this one, but essentially when you find parametric anything, it eliminates a variable. Remember that back from like Calc 2 when you were like, hey, here's x's and y's, and you define them in terms of t. X and y's both change to t's. Now we're saying, well, we got x's, y's, and z's. Let's define them in u's and v's. We've already done that, 14.8. Transformations, remember that? Kind of did that sort of thing already. This is just kind of a further, just a little bit further. And those were surfaces. We're just kind of redefining the same thing. It's just, hey, if you could define something that has x's, y's, z's, where x would be u's and v's, and y's would be u's and v's, and z's would be u's and v's, and you know that vector functions are always the x component I, the y component j, the z component k, then what we can do is we can redefine the surface itself as the vector function. And it would give us the same thing graphically. Here's what I want you to get out of this, all this notation. It's saying, I'm essentially just going to be changing x component into something with u's and v's, y into something with u's and v's, and z into something with u's and v's. Therefore, I can define a vector function in terms of u's and v's, u's and v's, u's and v's. Does that make sense? 3 variables change to 2 variables, that makes things nice for us. It also makes the formulas even nicer than these ones, because these don't look very nice. I'll show you how to do that. Are you guys okay with the notation so far? Now I'm going to give you 2 examples on how to do this. The first one's very easy. It's supposed to be very easy. I just want to get your head wrapped around it. So let's suppose this. Hey, let's take a look at it. What is it? Well, how about this? Surface, yes or no? What do you think?
Yes.
How many variables?
3 or 2.
3 variables.
3.
3 total variables. X is dependent on both y and z. Head down if you're right with that one. This is half a cone. If you didn't know, that's half a cone. Upper half cone along the x-axis. Remember cones at all? Square both sides, you get x squared equals y squared plus z squared. Means if you solved it, you get 0 and you get 1 negative. It's along that axis. But this is an upper half cone because you got a square root. You're not taking the bottom half of that. It's upper half cone. Head down if you're everything on that one. So, here's how there's 2 cases. One case is way easier. This is the easier case. Please listen carefully because it's going to save you a freaking ton of time, okay? A ton of time. If you have a surface where it's already solved for 1 variable. Is this already solved for 1 variable?
Yes.
Okay. Then it's already depending on only 2 variables. It's already there. Then what you do to parameterize this, call this u, call this v, and it automatically takes care of x. It's the easiest. It's a trivial parameterization, but it lets you put this in vector function notation. Does that make sense? You can honestly do it right from here. You could literally do it with x's, y's, and z's. But if we want to use u's and v's, here it is. Write this down. For functions already solved for a variable, let the other variables be parameters. It's going to make sense when we do our example. If it's already solved for x, then the other variables are y and z. Those variables become your parameters. Doesn't matter which one. No, not really. Pick one to be u, pick one to be v. So let's say, hey, x is solved for y and z. My other variables, the ones that are not solved for, are y and z. Let's let y equal u. Let's let z equal v. Head nod if you're okay with that. Yes, no, yes. Okay, then what's x? Well, x doesn't really change. That's why it's trivial. X doesn't really change. Then x is just going to be the square root of u squared plus v squared. If y is u and z is v, then x is just u squared plus v squared. You're not doing any. That's why it's a trivial substitution. But what it lets you do is easily redefine a vector function in 2 variables. Are you guys okay with the x, the y, and the z? Okay, so let's continue. Every vector function ever does the x thing, I, plus the y thing component, j, plus the z component, k. And since we already have that, yeah, it's trivial, but we've already redefined it. Now we can easily define our surface parametrically, and that's exactly what this means to do. Define as a vector function, those are our parameters. So let's define it. What would this first part be? Can you tell me that, please?
Square root of u squared plus c squared plus I.
What would the y part be?
U.
What would the z part be? I don't know if that makes sense to you. But by the way, in case you didn't see it, I keep using this word trivial. Trivial means it's really not doing a whole lot for you, and here's why. If you just called this y and z, you could have y and z and y and z, y and z. It'd be the same. We typically change variables just so you're showing that you have a different parameterization. And so it fits our notation a little bit better later, honestly. But we're not really doing much. So this is did you guys see that it's a really easy case? It's a really easy case. If you're solved for one variable, the other two variables become u and v respectively, and just plug it in. That's all that's happening. Show of hands if you're okay with that one. Now, a little more difficult is when they're not solved for. We're going to do one of those things, and then we're going to work with it. Do some examples with this. So, are there any questions on this right now? Okay. So let's give this one a go. Ladies and gentlemen, is this solved for one variable? Yes, no? No, clearly not. You got x squared, y squared, z squared. Here's my first advice to you. Don't solve it for one variable. Because as soon as you start taking square roots, you lose half of this cone. This is another cone, but it's a full cone. Do you guys see that? It's a full cone along the z-axis, actually. And if we took a square root, we'd be losing half the cone. Did you guys get it? That'd be a problem, and I want to do that. So, when you don't have a function that's solved for a variable, you're going to be using a non-trivial parameterization. How to pick it? Start with one side. Parameterize one side that looks like it's easy to parameterize, and it's awful wording. But start with a side that has the majority of variables, all but one variable. If you have to move stuff around, maybe move stuff around. I'd start on this side. So when you're not solved for variable, parameterize one side and use it for the other side. What side do you think that you would want to start with here? Would you want to start with the z squared side or the x squared plus y squared side? Why? Why would you want to start with the x squared plus y squared? What's that look like to you? It looks like it's something that you could call something else. That's why we start with one side. Something that you could call something else. That rings a bell in your memory. You go, hey, x squared plus y squared. Have we ever defined x squared plus y squared before? What do we typically call that? We can do things like that. So let's call this... Let's let x squared plus y squared equal r squared. But I told you something about 15 minutes ago. I said as soon as you do that, you're picking some very specific things for x and y. Do you remember that? You can pick any two variables you want to be x squared and y, well, to be r squared. But we specifically chose x and y to be x squared plus y squared equals r squared. Does that make sense? It means x and y have to be two very specific things. As soon as you do this, as soon as you make that connection on one side, you have to label what they become. So what are you going to call x?
Cosine theta.
Exactly. And what are you going to call y?
Cosine theta.
Do you realize that you just parameterized x and y in terms of two variables, r and theta? Are you guys okay with that one? Now let's work with this. If we called this r squared, then that also means that r squared equals z squared. Or r equals z. I'll write that over. Z equals r. So I have, hey, look at that. I've got x and y defined in terms of two variables, z defined in terms of one of those two variables. I've literally redefined x and y. We have literally redefined x and y and z. That's parametric. That's how we would redefine the surface parametrically, at least the start of it. Are you guys okay with the idea behind it? So if it's solved for a variable, it's pretty easy. If it's not, pick one side and start doing things like defining x squared plus y squared equals r squared if you can. Work with that. As soon as you do it, redefine those variables. Now, I don't even have your attention. I should have your attention because it's important. There's two things going to go on. As soon as you have this, and you know this, right? You know that we're trying to get down to this. The x thing I, the y thing j, and the z thing k. Oops, that's not a k. Not okay. K. We're trying to get down to that. Now there's two issues we're going to have. Do you see one of the issues? You don't see one of the issues. What variables do I want? What variables do I have? Could you just define this as r and theta? Yes. But it looks a little weird because we're going to have a lot of r's floating around, okay? So I really don't want to use a vector function of r and then have a variable of r inside of it. Does that make sense? That looks a little funky. Can you do it? Sure, you can do it. It doesn't matter. U and v are dummy variables. They don't even matter. Just pick any two variables and you've got rid of one variable at least. So r's and thetas, fine. But I wouldn't pick them because I don't want to run into confusion. Now, should there be confusion? Not really, but you could do something really easy. If you just say, well, let's let r equal u, and let's let theta equal v, then we just redefine this thing. Does that make sense to you? So we go, okay, well then, x is going to be u cosine v, y is going to be u sine v, and z is just going to be u. And now that matches our notation a little bit better. Again, does it matter? No, it doesn't really matter because they're dummy variables, but they're going to fit your formulas a lot better because our formulas are based on u's and v's. If you have r's and thetas, you're going to have to make that transition in your head every single time. Should finish really okay with that one. Okay, now, what I want you to do right now is take what we've done and build your vector function out of it, please. What should go here? Quickly, please. What should go here? Perfect. Love how it still has an I. Plus what? And? Yeah. Here's the point of all this. This will give you the same cone that gives you. It's the same thing, which means anytime I want to use this, but I don't want to use three variables, I'd either have to solve for z, or I could reparameterize and do the same exact stuff with it. Show of hands if you're okay with that one. Well, leads us to the next question. What if you have chosen to parameterize your surfaces? Well, wait, that stuff's all in regular functions. Can we still get this stuff from these type of surfaces? Yes. Yes. There's a slightly different way that we can talk about surface area. So I need your heads wrapped around this. Firstly, I've only given you two examples, but they illustrate pretty much how to do this. Are you guys okay with parametric surfaces? How to take a surface and parameterize it. I give you two ways. Most of them fall into one of these two categories, where either they're solved for variable already, piece of cake. And if they're not, pick a side. And then as soon as you pick a side to parameterize, then the rest of it just kind of flows. Then you create your vector function, x, I, y, j, z, k, and you're basically done. You guys are right with that one? So let's suppose that you've done that. So you got this vector function, looks like that. And it's a surface. Then there's another way that we can talk about surface area. The second way we can talk about surface area would be this. Now imagine, okay, you just did all this work and you have this vector function represents a surface. What two variables you got? Could you take a partial derivative with respect to u?
Yes.
Could you take a partial derivative with respect to v?
Yeah.
Could you cross product those vectors that you will be getting with respect to u and v? Yeah. Could you take the magnitude of it? Yeah. Here's the nice part about it. Here's the cool thing about it. The D. So what this means is very, very similar to what we did with this stuff, where R is the projection onto a plane. D is just the bounds of your parameters, u and v. That's all it is. So D is basically, you can call it domain of the parameters u and v. I don't really want to round. Do you understand that's the notation for the partial derivative of the vector function r with respect to u and with respect to v? Same like that was the same for g. What's dA going to have to change to? Yeah, it would just have to be du dv because our variables now are just du dv. Is that all pretty straightforward to you? Because I'd like to do an example here real quick. But I want to make sure that we're good on it. Are we? Are we okay with it? Am I losing you? You falling asleep? Need some wake-up juice here. I know we've talked a lot, but the idea was, I'll answer your question in a second. The idea is, hey, if you can parameterize surfaces, can we work with that? Yes. Now have your eyes on the board here real fast, please. Put down your phones or your whatever you want. Just put it down and listen. What is this? This is the surface area. This is the surface area of whatever this vector function gives you. Does that make sense? Look at the board right now. What's the mass density function? What is the mass density function? Is there a mass density function? What is the mass density function then? 1. We're right here. Look at the board. We're right here. Do you see it? Same thing. We've just defined our surfaces parametrically. Same thing. In fact, look! I'm begging you to stop with what you're doing and look at the freaking board. I'm begging you. Do you have to beg? I'm gonna beg. Stop and look. How do you find a magnitude? Practically the same thing. You're practically doing the same. Squaring them, adding them, squaring. It's the same thing. You're just doing it parametrically. That's all that's happening. Your mass density function is 1 giving you surface area. Oh, wait a minute. So how could we go about and change this into getting a surface integral with a mass density function? What's going to go right there? A mass density function defined in terms of u's and v's, and we make the jump. So right now we have basically 14.5 again, but just with parametric surfaces. All we're doing is finding a magnitude of a cross product. That's a vector. Find the magnitude of the vector. We're basically getting this surface area idea again. If we put a mass density function right there, we'll have a surface integral, finding the mass of whatever the surface that vector function defines. Is it making sense? You see the connection. I can't have it be separate. I've got to have it be the same exact idea, just a slightly different way. Should finish okay with that one. And so I teach it this way. It's got to flow. You can't just say, oh, parametric surface, that's a long time ago. That doesn't make sense. It's the same stuff. Okay, it's the same stuff. Now, what I'd like to do, we'll probably just do one example, and then, I'll show you show you what I was just talking about, and then take a break. So what I'd like to do right now is find the surface area of the cone that we just parameterized. Okay, so I want to do that. So let's go through it. Hey, find surface area of this thing. Could I write that in terms of a function z? Yes, but I have to take a square root. And I don't really want to do that because I might lose half my cone. Is it a problem? Well, maybe, maybe not. You could always double it if it's a symmetric cone, probably double it. Could I do it a different way? Yes, yes. Can I parameterize that surface? Yes, in fact, we've already done it. I don't want to go through the process, but we just did that. That was why I did that example. So this says, okay, if I define this in terms of this, almost, and this, I'm going to write a little side note, just so, because later on I'm going to come back to this, I'm going to prove it to you, okay? Just a little side note. Remember that R was U and theta was V. Just keep that in the back of your head, okay? I want you to remember that for a while. So if that's our vector function, here's the first thing I need you to see. Do you recognize that this is the same full cone that is? Do you guys see that? It's the same exact thing. So let's start working with this and treat it as a vector function that defines our surface. Can you find the partial derivative of this thing with respect to u? Okay, let's write that down. Tell me what it is.
Cosine.
And?
Sine.
And?
Okay.
Cool. Oops. Can you find the partial derivative of this with respect to v? Can you do that? A little bit more complicated because you got some trig function up there, but we should get negative u sine vi plus u cosine vj. And that's it. There should be no k because there's no v component of that. Head nod if you're out with that one. Okay, what's the next thing? What might you do here?
Crosses.
Set up a cross product and see if you still know how to do that. Good practice for our final coming up. Hopefully you made it that far. Did you make it that far? At least the setup. Do y'all remember how to do it? If you remember how to do it, it's kind of a cover-up method. I cover up this. We multiply, subtract, multiply. So multiply 0, subtract and multiply negative u cosine v, and then we have an I. You guys okay on the negative u cosine v I? Did you get the same thing? Next thing, before we do anything else, what's the next sign?
Minus.
Make sure we're okay with that. Minus, okay, cover this up. Multiply, that's 0. I'm going to show this one so we don't get all screwed up on it. Subtract and multiply gives us minus a negative. That would be plus u sine v j. Are you okay with that one? Okay. Lastly, we got a plus. Then we go, okay, well, oh, yeah. Bless you. Multiply, we get u cosine v squared. Or cosine squared v. Minus, well, if I subtract, I subtract a negative here. So plus u sine squared v and then k. I'd like to show of hands, feel okay with the cross product, feel I'm done. Yes, no, yes? What now?
Take the magnitude.
Before that,
Simplify.
simplify as much as you possibly can, because I don't want you to start in magnitude if you haven't simplified these pieces. What's going to happen here specifically? Factor the u, cosine squared plus sine squared, v is, so this is just u, simplify that. Now, find the magnitude. Remember, with magnitude, we square the components, add the components, and square root them. Try it. Hey, are we going to have some simplification that's going to be taking place? What do you think? They all got u squared. Factor out a u squared. You're going to get a cosine squared plus sine squared. That's going to give you 1. But then you also have another 1. Can you guys see that this is going to give you a 2u squared inside of this square root? If we simplify a little bit further, then this is simply square root of 2u. Now, what is that? That's now the argument of your surface area. This is the only thing that you're going to have. That's it. That's all you got to do. And so I want you to set it up. So right now, all I want you to do is take this piece, put it in there. Do I want you to deal with the D? No. Do I want you to deal with the dA? No. I just want you to set it up. So the whole idea here is if you can parameterize a surface, find the partial derivatives, do a cross product, find the magnitude, all the hard work is done, just set up the double integral. I'm going to have to erase this again. I wanted you to see, well, I guess you kind of saw the connection there. I want to make one more connection. But I'm going to erase this here real quick. Are you guys okay making it this far? So when everything's all said and done, don't skip this step. We have 2 square root u dA. Yeah, that's not the same thing, is it? Good thing I have you guys here. Thanks. So I'm going to miss you. So I'll miss you all when you're gone. Other classes, they just let me go. And then 20 minutes later, go, thanks a lot, guys. Appreciate you're paying attention. I failed them all. Anyways, not you guys, though. You're all getting A's. No, that's a joke. Is that me? It doesn't happen. Yes, unfortunately. But there are a lot of A's. It's good, especially on the third test that I have for you. You didn't even know that, huh? Yeah, it's good. Anyway, what do we do now? Well, D. What D is the domain for our parameters, U and V. This is why I had you write this down. I want you to look at this. If this thing's a cone, okay, if this thing's a cone, and if U equaled R and V equaled theta, to go full circle around that cone, our theta would go from where to where? If I wanted to go along the R, well, I have a choice to make. Look carefully. Please listen. Remember, this is surface area, right? And we're dealing with a cone. So this is finding the surface area of a cone. That's it. If I just stop at any R ever and go full circle, it would give me the surface area for whatever cone I want with a given radius. Does that make sense? That's what it would do. Well, what if I let the U, because again, U is the radius, that's all it is, go from 0 to R. Then what it would give me is a formula for the surface area of a full cone. That's what we're talking about here. So again, if I went from 0 to 2 pi, that's just going full circle around the cone, okay? If I went from 0 to like 4, it'd give me the surface area for a cone that stopped at a radius of 4, from 0 to 4. Does that make sense? If I went from 0 to R, it'd be 0 to anything. I could plug in R later and find a formula for the surface area of a cone. This particular cone, root 2 U, oh my goodness, you're going to see some magic happen. What has to go first? D, U, D. Where'd the U come from? R. Where'd the V come from? Say it. I'm not going to say it for you. R. R. DR. What? That's crazy. Magic. Coincidence? There are no coincidences in life. No. Could you integrate that?
Are you missing a U right there?
No. Are you missing a U right there? I'm not missing U. This dA, this is just du dv. I'm not changing to polar because I already did. I already did it. That's the whole nature of letting u equal r and v equal, it is polar. You can see it. It's already there. It's right there. It's already done. It's just in the vector function itself when I parameterize it. It's right there. It's right there. Now, can you do the integral from here? Mm-hmm. If you did, not too bad. Let's see. I guess we could do this one. Yeah, I think. Make sure my work's right. I don't mess this up. Looks like we got r squared dv. Now wait a minute. I thought that we couldn't end with a variable r, but keep in mind, that's why we chose u instead of r. If I want to go from 0 to r, I need to plug in r for a different variable. This very well could have been a constant. It is a constant. I'm just getting to plug in the constant later. Do you guys see why we chose u instead of r? That allows us to plug in r into something that's not r and get a formula for this with respect to r. So dv would give us, well, just v, this whole thing v, where v goes from 0 to 2 pi. Okay, well what's that mean? If I plug in 2 pi and subtract 0, I get 2 pi. 2 pi times 2, that's just giving us the square root of 2 pi r squared. I want to know if you're okay with the math behind it. Now what is it? Is it mass? Is it mass? No, what is it? Surface area. Of what? Of the cone. Of this specific cone, please. Please watch. This is surface area of this cone. Are there different cones? Of course. This is surface area of the specific cone. Does that make sense? For however far I want the R to go. Now, what if we do it a different way? How about this? Check this out. If that's a cone, and I go, well, if I let this equal r squared, which I'm going to do that. So I want you to check. Here, watch. If you look up surface area of a cone, Like Google it or something. You get that. You get something like that. Okay, well, how's that relate? Well, I'll show you. If I think about this cone is along the z-axis. Are you seeing what I'm talking about? That means that z is the height. Z is h. Are you following that? Okay, so z is h. But wait a minute. Z is also, or z squared, I guess, is also x squared plus y squared. So if z equals h, and z also equals the square root of x squared plus y squared, then this is the square root of r squared, and this is r. If z equals h and z equals r, then for this particular cone, h is the same as r. It's like a cone that has the slope of 1. It's making like a square. That's basically how the diagonal would be making a square out of it. So for this particular cone, if z equals this, and this equals r squared, then z equals r. But if z equals h, then h equals r for this formula. I'm going to move over here for just a second. So from here we have r squared, yes. H squared, no. Since h is z, z is r, that would be r squared. You go, well, wait a minute, that looks pretty nice. Pi r square root of 2r squared. You go, hey, what's square root of r squared? Well, it's r. Surface area of this cone where z is the same as r, z is height. Surface area of this cone where z is height. Same surface area. Done geometrically, done calculus-y, done either way. You get, that was funny. Come on, lighten up. Get too stressed out. Take this stuff too seriously. I just wanted to prove that this is what we're actually doing. Okay, this is real stuff. It's not fake stuff. I'm not making this up, even though I wish I could make it up. It'd be freaking awesome. I've only done it one time. Okay, it was just a fake lesson. I got really in trouble for doing it. Never do it again. But this is real. It actually makes sense with geometry. It's analytic geometry. Okay, yeah, we're doing geometry calculus-wise. I'm gonna leave you with one thing, and then we'll come back and do an example. You know what? We'll take a break now because I think we need one. We need to let our heads get refreshed a little bit. We'll come back and we'll say this, and I've already said it. If I can do surface area with this, I should be able to do surface integrals with this by just putting in a what here? Yeah, I should be able to find surface integrals and find the mass of this surface. We'll do that later. Okay, so hey, you know, we're going to make the jump. Right here, what I told you before was, and this is the only reason I left on the board was, if this is 14.5's version of surface area, which it is, and this is our now surface integral where that's a mass density function, then we should be able to make the jump here. If this is surface area of the surface parametrically defined, and we just take and put a mass density function right here, then we have surface area, the idea of mass at every point across the surface, and add it all up, and this should give us the same thing that this does, which gives us mass of a surface if that is the mass density function. Show of hands if you're okay with that one. So just like we've done surface integrals before, now we should be able to do them parametrically as well, and that's what we can do. So parametric surface integrals look just like this, do the exact same thing as you would do for surface area. It's just now you also have to, man, that looks a little weird. That looks a little weird. Well, that just means that you're redefining your function in terms of the pieces that are given to you right here. I don't know if you're okay with that one. Now, I've given you kind of an easy example. Someone, and it's not generally easy to do, someone has already defined your surface. Look at this. Look. Do you guys recognize that's a surface? It's a vector in two variables. It's giving you a surface there. This is a surface. Someone's given it to you. They're also giving you the domain for u and v. That's really convenient. Here's what I want you to do. Firstly, recognize you are going to have to change all of your variables into u's and v's. Do you guys see that? You're going to have to do that. So right here, you're going to need to find out what x is, what y is, and what z is. So if you're given a surface in terms of this parametrically defined surface or a vector function, I want you to just right above them, write what x, y, and z are. That way we can make a little substitution later. So what's the x thing? And this is y, and this is z. You guys okay with that one? Then we just run through the formula. What we're going to do here is, well, now let's be real careful. Is this the surface? No, I'm not. I'm trying to kind of see if you're with me on this stuff. That's the surface, guys. What is that? If this is 1, then this formula gives that thing. Does that make sense of what I spoke about earlier? If that's 1, then we just get surface area. If it's not 1, that's a function based on what the points are. So this all has to change to this stuff based on x, y, and z. We also need to still find this in the formula. So how I would start this, I'd start with these two things. So find the partial derivatives, cross them, find the magnitude. That's what I want you working on right now. About every 30 seconds, I'm going to put a step up on the board. It's going to take us a little while. I'm going to erase this since I made my last connection to it. I'm going to start working mostly on that side. So I want you doing just two things right now. I want you finding the partial derivatives and crossing them. If you've made it that far, then I want you to start working on the magnitude. Hopefully you got at least your partials correct, and now start to cross them. That's -1, -1, k. Ooh. Check my work, see if I'm okay. Are you guys okay? Did you get the same thing?
Yeah.
Okay. Now, goodness, what do we need to do? What now? How?
Combine
Find
negative
that two minus.
Okay.
Then maybe distribute that negative sign.
You could. If you want to, you could. Now what?
Magnitude.
Work on the magnitude. That's what I got for the x components squared. So we square them, we add them, and we square root them. I got that when I squared that thing. Can I get a double check? Did you get the same thing? I got that when I squared that. And just 4 when I squared that. Head nod if you're okay with that one. What now?
Okay,
Simplify a lot of stuff.
Yeah.
Also, you know, everything's got a 4 in it. Just factor out that 4. If we factor out the 4 from everything, we get
2 squared.
hopefully that. If I did my math right. Did you get the same thing? What can you do with the 4?
Square root.
Yeah, because it's now multiplication because we factored it. I'm also going to factor this. You'll see why in a second. Make it just a little more concise. So the 4 squared 4 is 2. Factor 2 out of this, but not that one. So we have this 2 times the quantity u squared plus v squared, and then plus 1. So things we all the algebra on that one. What now? What now? What do you think? Well, what have we done? We're trying to figure this out, right? We're trying to figure this out. What we've basically done is just figured this. Right now, this is this part. Surface area, surface area. That's basically it. Let's start setting this thing up again. Don't worry about your region, your domain right now. We'll deal with that in just a second. Right now, I want to see your setup on your double integral. Start with this first. Change this stuff accordingly. I'm going to give you about 30 seconds to do that. You guys okay with what I'm talking about? What needs to happen to all the x's, the y's, and the z's? We got to be using v's. Can we do it? Thankfully, yes. Come on, try it. If you haven't done it, try it. You got to try it. So I got this, I found the cross product, we found the magnitude, we simplified as much as we can, and we have it right there with the dA. That's exactly the same thing. This piece, this says, look at the mass density function in x's, y's, and z's. Use your parametric surface to change it. X becomes this, y becomes this, z becomes this, every place you see it. So in our case, we have x minus y over nasty square root the 2 doesn't change, but the z changes. 2 times z. What else? Hey. I want to see if you can make it that far in your minds right now. Can you guys see where all this stuff is coming from? Why are we changing x's and y's and z's again? Could you even do the double integral if I didn't do that? We'd have like 5 variables. We'd have u's and v's and x's, y's, and z's. That's crazy. So we're using our parameters here to change our mass density function. That's legal. It's on this surface anyway. We're talking about that. What now? What could you do now? Simplify before you even worry about your region or your domain here. So this is gone. Tell me what else you could do. So this all becomes U's gone. You get what, 4V? That looks a whole lot nicer than what we just had. A whole lot nicer. Now go back and fill out your double integral. So all this stuff, all of this is just setting up your double integral. That's what I'm talking about. The setup's the most important part. Once you get this, you have a very simple region. In fact, if you look at the region you have here is, what type of region is that? Where U and V are both, say it louder? Rectangular region. Set up any way you want. You can do du, dv, doesn't matter, as long as you go constants. I would go du first, and then dv, also, so I don't have to deal with that v. So I do just a u, integrate, done. Question?
Is that supposed to be dA?
Yeah, I'm sorry, thank you. It is supposed to be dA. I got ahead of myself. Now change it. So I'm going to do 4v, I'm going to do du, then dv. I avoid integrating this with respect to a variable that's up there, so I want to do du. I want to go from u 0 to 1 and v 0 to 2. Should finish all right with that. Easy, medium, hard. Plug some stuff in, you end up getting 8. Now what is that? What's the 8? It's the surface area or not? It's the mass. It's the mass of this parametrically defined surface between these numbers. Between u goes from 0 to 1 and v goes from 0 to 2. That's what it's giving. The mass of that surface, that plate that's been stretched into a surface. That's what's happening here. I don't know if you're okay with that one. Kind of cool, right? Now, the next question, if you want to go back to what we did. We did line integrals. Then we said, well, let's put a line integral through a vector field, and let's see what happens. Now we have surface integrals. We got to see what happens when we put a surface through a vector field. So we're going to talk about surface integrals on vector fields. That's what we're going to start discussing right now. So I want you to think about it this way. Think that a vector field, or think of a surface on a vector field, so that vector field contains the surface. That's why it's got a couple things about that. If F, let's call that a vector field, contains a surface, then F describes the velocity of the flow or the fluid. We talked about that. Remember talking about vector fields, how they describe like the flow of fluid or some substance at any point across the surface. So if our vector field contains a surface S, then the vector field describes the flow or the fluid or the velocity of what that flow or fluid's doing at any point across the surface. Why am I using the word velocity? What two things does velocity have?
Speed and a direction.
Good. So basically just a vector. So vector fields describe velocities. That's what they do. So what F describes, the vector field describes, is the velocity of the fluid or the flow, however you want to think about that. At any point across the surface. You know, it's kind of like before. We had that. It's just right now we don't have just a flat plane. We don't have that. We don't have a flat figure. Right now we have this surface that's going through a three-dimensional vector field. By the way, I get to describe something for you. The rate of flow, so the amount or the volume of the flow going across the surface, is called something called the flux. It's also called flux. Now we're going to deal with something, but I want you to hang on to this idea. Can you do that for me? Hang on to the idea of the amount of the flow going, or the volume of the flow, the rate of flow across the surface. What's that called again? I want you to hang on to that idea. Like that one thing in like electricity that holds on to charge. What's that thing called? That's right. I want you to be a capacitor for the. I want you to hang on to the flux. Be a capacitor for the flux. Be a. You got it. Boom. Had to throw one more in. It's the last lesson. I'm pulling all the stops here, guys. Can't use it later, man. It's the last video. You got flux capacitor. Dang it, that's good stuff. What? I worked on that all day, just for this moment right now. It's like lesson prep, jokes. That's what I'm doing. Cheesy, Back to the Future jokes. Seriously though, it's called flux. I'm not gonna make that up. So let's talk about the flux. Now let's think about this. The flux is given by. I'm going to give it to you. I'm going to show you why it makes sense. The flux is given to you by this. The vector field dotted with the normal vector surface area. You go, well, what's that? What's this really mean? This is a vector field. Dotted with the normal at any point of that surface. Not cross, just a little times multiplication. The area of a really small piece of the surface. So surface area. What's it given us? Well, it's given us a normal to that surface and the flow through that surface according to the vector field. So it's given us how much is crossing this region. This is the idea here. Think about the idea, please. Listen. Normals go through stuff, right? Okay, so if you had a surface of normals going through that. It says, okay, vector field's describing that flow. I take a dot product. This is the amount of the flow times the size of that region. Basically, this is the amount of the flow going through a little teeny bitty region. Now, we want to do this for the entire surface. And then we want to add it all up. What adds up stuff in calculus? Integrals. So surface is two-dimensional idea over the region. Think the region. Two-dimensional idea. We're going to be adding up all the flows across little bits of surface. That's what this is called. It's called a flux integral, or typically we call it that. So this would be a surface integral through a vector field, or we call that a flux integral a lot, because what it's describing is the rate of flow or the amount of the volume that flowing across the surface. And now if you're okay following the idea. So if we do this for the entire surface, well, then we have a surface integral changes a little bit. So we'd start saying, well, if we can describe this as, I got to make a little fine point here. See, if we want to do a surface integral where our surface is going through a vector field, that's what this says. A surface integral through a vector field. We go, well, what are we going to do? We're going to think of this as the vector field dotted with a normal times a really little small part of area. This is the amount of the fluid going through that area. That's what this means. I need to make a little point here. Much like the switch between f.dr and f dot that r prime dt, this s is it's a slightly different s. Notice the difference. Dot product has to happen between two vectors. Do you see it? These are two vectors. This includes the vector portion of it. This one does not. This is a dot product between f and n. This is just the idea of the area itself. It's not a vector. It's the difference between a vector and a scalar. Does that make sense? It's slightly different. Now, fortunately, we don't have to deal with this a lot. We're going to make another jump here in just a second. But the idea is this idea. The idea is we're finding the flow that's going through a surface, a little teeny part of that surface, and then we're adding up all that flow. And that's giving us a flow through the surface over a given region there. Hence if you know it, you understand. So this is the idea. This is called a surface integral through a vector field, or we often call it a flux integral. Why? Because it describes the flux. One last statement, then we get to the kind of cool part. How to do it. You know, I hope that you're kind of sticking with the idea, because a lot of calculus builds on this idea of the same idea over and over again, we just apply different things. When we had a double integral of 1 dA, that was just area of the flat region. Make sense? Put a function in there, you're finding mass of the region. You get it? When we had surface area of mass density function 1, which just had it, that's giving us, well, just the surface area of the surface. We put a mass density function there, we get the mass of that surface. This right here is just giving us the amount of flow through a surface, across a surface. Does that make sense to you? What if that flow has a mass density function? Then it would give us the mass of the fluid crossing that surface. Does that make sense? So if I want to find this, so if the fluid or the flow has a mass density at a given point, okay, please watch carefully. I want you to get it. I really want you to see the scenario play out for you. The same like double integral over a region with 1 and versus a mass density function. Surface area with 1, and then the surface area with mass density function. What's this give you? What's that called? That's a flux integral, so this is describing the flux, the amount of the flow going through that surface, whatever that's defining. I don't know if you're okay with that one. Then that gives you the mass of that fluid. Does that make sense? It's very similar to the previous concepts we've had. Amount of flow, mass of flow. Get it? Like amount of area, mass of the thing that's occupying that area. Very similar idea. So this would give you the mass of the fluid flowing across the surface S. Now, how we actually do it. Obviously, I'm going to have to define a few things for you, right? Anytime we do this stuff through a vector field, you need to know what the vector field is. It matters. You also need to know what the surface is. It matters for right now. So we need those two things. So let's define a vector field. It's just like normal. Pi, Qj, RK. So just a function-defined vector field. Hit on if you recognize the idea of a vector field. So that's our vector field. Then the flux integral, this is where we started. This was a surface integral across a vector field. That's what we started with. We said, well, this equals this. This is a surface integral, and we changed it a little bit. We said, yeah, that's the same thing. We talked about that. We go, okay, here's how we actually do it. There's a formula. I'm going to just state it without proof, but it's going to make your lives really nice. Here's how we actually compute. And the proof, I believe it's in most of the Calc 3 books out there. You can just check the proof out. It's not beyond you. It goes back to some summation notation. Just adds up the little areas. If you've made it through the other proofs in this class, you can look at it. You can do it yourself. You really can. Just take a look at it. Involve some cancellation, simplification. But it's not beyond you. So here's how we do it, though. Do we get wrapped up with this? No. Or this? No. Here's how we do it. If we're trying to calculate the flux of a vector field across a surface, we can use this formula. It's going to look kind of nasty at first. Don't worry about it. I'll show you where everything comes from. Negative P. Where's the P coming from?
The mass density function.
No, the P, not the rho. The P. Where's the P coming from? That's what the P is. It's just the x component of the vector field. They put a negative in front of it. Does that make sense? What's that mean? Partial derivative of g. Where's g? This would be for a surface that's defined z equals a function x and y. So we start off with x component partial derivative with respect to x. They match up. Make sure they match up. Minus, what do you think the next thing is going to be? Just use your intuition. What do you think the next thing is going to be? Q. And a partial derivative with respect to, what do you think? And lastly, can there, if I've defined the surface as z equals a function of x and y, can there be a partial derivative with respect to z? If there is, it's 1. There is none for z. It's defined as a dependent variable, dA. Over, I need to explain this to you, please. I'm going to use the letter D here. The The letter D, listen carefully, please. I don't want you to lose this. The letter D is the letter R. It's just the region. It's the projection of the surface onto the xy plane. Why the xy plane? Because we define this as z equals x and y. Does that make sense? It's on the xy plane. I can't use the letter R because it gets very confusing with that letter R. Does that make sense? You want to avoid that when you can. You don't use the same letters. So here's what this says. If you want to calculate a flux integral, all you have to do is this. You need a surface, which you'll have. Just solve it for z. You'll need a vector field, which you'll have. Literally, p, q, r, partial derivative with respect to x, partial with respect to y, you're done. And just look at what the projection of your surface is doing on the xy plane. And now if you're okay with that. That's it. Now, what's the time? Oh, we got some time. Sweet. Let's do at least one example, and then we start getting into this is crazy, the last two theorems ever for you guys. It's so nuts. Oh my gosh, it's blowing my mind right now. It's so great. After all this work, we're coming down to the last part. So, did you catch what D is? What's D again? The projection of this surface onto the xy plane. So let's give it a try. Okay, let's give it a try. We gotta find the flux of the vector field across the surface, which is the surface bound by those two functions, where the flow is described by that vector field, xi plus yj plus zk. Do you guys understand the idea of what we're about to do? So we're trying to find the flux integral. That's going to give us the amount of flux there. We're not talking about mass here, just the amount of flux across that surface given by that vector field. Make sense? That's what we're doing. How you start. Number one, write out what you're trying to do. Flux. A flux integral is originally that. It's a surface integral through a vector field. That's all that's happening. But we have a formula for that now. The formula says, okay, this is the idea, but the how we do it says I want to find P times the partial derivative of g with respect to x minus q times the partial derivative of g with respect to y plus r and then dA. This is our goal. This is what we're trying to find. So right now, what I'd like you to do, what I want you to do is from your vector field, you should be able to identify P, Q, and R. It should be really easy right now. Can you identify P, Q, and R? Maybe just write a little letter above them. This is P, this is Q, this is R. Your vector field always gives you the P, the Q, and R. Head nod that you're with me on that one. Okay, next step. we also need a surface, and we need that surface to be defined for us as z equals something in terms of x and y. Do we have one of those? Okay, so which one does this one? This one.
Yes.
Okay. What about that one? Does it matter for us so much? It's not going to matter right now, but it's going to matter for the region. It's going to matter for, I'm going to call it the region, that's what it is. We just have to use D because I don't want to mess up the R. So that is our region. We're going to do that later. Again, it's all about the setup first, then you look at the region. So let's just find the only function up there that has a Z in it. That's the function. So let's let Z be a function in terms of x and y. That means for us, Z is this function, 1 minus x squared minus y squared. Are you okay with that? Hello, yes, no?
Yes.
Okay. Well, if Z's our G function and Z equals this, then our function in terms of x and y, it's just exactly the same thing. But it allows me to use this stuff. It allows me to take partial derivatives with respect to x and y. Notice there's just x's and y's. So I want to, right now, find the partial derivative of g with respect to x. Can you do that? Is it really easy?
Yeah.
What is it?
Negative.
And again, with respect to y,
Negative 2y.
that's it. So the vector, look, it's nice. The flux integral is nice, okay? You take your flux integral, but you've got a nice formula for it that's given by a super cool region, just a projection onto an xy plane. You have P, you have Q, and you R from your vector field. You have G, partial derivative of G with respect to X and with respect to Y from whatever function is given to you. So we take our partials, just plug them in. See if you can do it. Once you take your values, plug them into that. By the way, have we even looked at our region yet?
No.
Don't even worry about it until you've simplified your double integral. Let's see, what should we have? What do we start with? I'm not going to do any simplification in my head. I'm going to put everything on the board because you know this about calculus. The biggest mistakes are sign errors, simple things. What do I have?
X.
I'm going to put in parentheses because I'm multiplying and you know it's negative x. Then what? Are you noticing the x components go together? Minus, what's the next thing?
Y.
Y from here, so negative, I have the minus. Y and then
Times negative 2y.
and then plus R. What's our R?
Z.
Are you still okay with it? Hello, yes, no.
Yes.
Let's do ourselves a favor. Let's start simplifying this thing. If we start simplifying this thing, then we have a double integral. Here's D, just our region. We got 2x squared plus 2y squared plus z dA. Are you still with me? I'm going to factor out the 2. Why? Because I want to. Now, you know enough about math in this class to know that there's something seriously wrong with this picture. What's seriously wrong with this picture? Why? Why is the z bad?
Because we're integrating.
Because we got 2 integrals and 3 variables. Oh, but wait a second. Which variable needs to go, x, y, or z?
Z.
Why?
We chose Z. We're on the XY.
Because you chose z as a function of x and y. Just plug it in. Just change your z. Whatever variable you have, hey, you should have a function in terms of the other 2. Change it. If z is this whole thing, What now? You can simplify it. Hey, you got two, this is one factored, by the way. You got two of these things minus one of those things. You got one of those things plus one. Yeah. Should fancy power with that one. Now, we did all of this work. We said, hey, flux integral or surface integral through a vector field, yes. We have redefined it by the formula that I gave you. We had vector field, we used PQ and R. We have a surface, we defined in terms of x and y. We took our partial derivatives, we plugged in the formula, we simplified. Now you have a very basic double integral over a region. All you have to do is look back at what's given your surfaces, and here's what's happened. You're going, hey, let's look down on top of the surface, look at what's happening between these two surfaces, and draw it on what plane? Come on, people, what plane? You're basically doing Z simple. Your R, your D in this case, should be on the XY plane. So D is on the XY plane. I want to show you something because some of you guys are going to try this. You go, wait a minute. This is the surface bound between two things, so you should clearly set them equal to each other. So if I have Z equals 1 minus x squared plus y squared, and I also have x squared plus y squared equals 1, then I should be able to substitute this. And so Z equals 1 minus 1, Z equals, oh crap, what happened? That just means that your intersection is on the XY plane. Which means that your level curve that you're getting there is literally on the XY plane. So don't fret. If it's on the XY plane, then Z is 0, just plug in Z equals 0, and you'll have a very nice picture of that. Does that make sense to you? So if your intersection is like, it zeroes out, what's that mean? It just means your picture's on the XY plane. So basically, just draw this, or plug in 0 and draw that, because you know what? You're going to get the same thing, because it's literally meeting on the XY plane. Does that make sense to you? So Z equals 0, whatever, that just means if this is 0, can you draw a picture of that? What picture does it give you?
Circle, region, circle.
Look at that. It's like this class is coming full circle. Yeah, told you. That's your D. That's your region. That's what that is. And if you're okay with that. So, what do you do with circular regions? This is why you don't define this stuff until you get your region. Because you can start doing all this work and trying to define X and Y, but you don't even know what it's going to look like yet. So you simplify all the way down and go, let's draw the region now. It makes our work a lot easier. Well, if this is R equals 1, and that's a full circle, then here's the point, though, that you need to do this. As soon as you let this equal R squared, as soon as you do that, then you're automatically calling X R cosine theta, and you're calling Y R sine theta. You have to have those pieces, okay? That matters. That's there. So if you have to use that later to change your stuff, then you need to have... I write it out every time, even though we're not going to use it here, you write it out. Because if you didn't have x squared plus y squared right there, if you just had x and y, you'd have to have those two pieces. I wanted to show you that. Does that make sense? So here we go, hey, we just defined this in terms of polar. Fix your double integral, please. Fix it real quick. What's this become?
R squared plus 1.
Yes, say that again louder. dA changes to what for polar? Don't forget your R. That means that we have to go R first, theta second. R goes from 0 to 1, theta from 0 to 2 pi. We have a full circle there. That's it. Can you integrate that?
Yes.
It's one of the easier ones. When you do, you should be getting 3 pi over 2. So thanks for that. Okay, what's it mean?
The amount of flux.
Yes, it says the fluid is flowing out of the surface at a rate of 3 pi over 2 cubic units per unit of time. How about this? Let's reverse the normal. It means fluid to be flowing into the surface. So normal is directed out of that surface, okay? Flowing out in all directions. If I reverse the normal, be flowing into this surface at the rate of 3 pi over 2 cubic units per rate of time, or unit of time. Last thing, I'm going to make one statement, and then the next time we'll talk about divergence theorem and Stokes theorem. So I'm just going to make it. We can also do this for parametrically defined surfaces. We are not going to do an example of this because I think you can handle it because it looks really, really similar. I want you to check it out though. So if you have parametrically defined surfaces, check this out. You wouldn't be able to really find this because you wouldn't have things in terms of x and y, u's and v's. So it's going to look really familiar. I want you to see the similarity. I want to do it now, so because I'll have all your brains kind of wrapped around it. Does that look familiar? That part. If you have a parametrically defined surface, well, it's going to be a vector function with u's and v's. You find the partial derivatives. You cross product. You do not take a magnitude. Otherwise, the dot product would not make sense here. You have to have the dot product, or you guys get what I'm saying. Don't take the magnitude, so it's a little bit easier. But then this vector field, hey, if your vector field is in terms of x, y, z, and you have this parametric surface in terms of u's and v's, could you use this parametric surface to redefine your vector field? Then this would have to be defined as whatever the parametric surface is defined as. The way that you would do it, you'd start off with your, it'd be, listen, we did this a few examples ago when we did a surface integral across, or with parametric surfaces. It's very, very similar. It's just now you get a vector field instead of that function. So you'd find, it'd be given to you, just find a partial derivative in both cases, do a cross product, redefine your vector field with x, y's, and z's in terms of u's and v's. Is it hard to do? No. And then you just dot product them and you do your integral. With whatever the d here is the same thing as it was before. It's the bounds for u and v. Show of hands if you think you can do that on your own. I don't really want to go over examples. Very, very similar. Just try it. Try it one time. So last little bit, we were right in the middle of something. What we were right in the middle of doing was taking these things called surface integrals and finding surface integrals of vector fields. Like saying, okay, well, what's that even mean? And we had a special word for it. We said, well, you know what? This is what the format is. We're doing a surface integral. It's a double integral of a surface over a vector field or through a vector field. Okay, so we found out that it's the same thing as a dot product of the normal to that surface at any point, dotted with the vector field. And then we said there's an easier way to do it, though. What if we took the pieces of the vector field, P, Q, and R, put them in this double integral, define the surface as z equals some function of x's and y's, took partial derivatives, then this represented the surface integral of a vector field. But what did that mean? What was that special word? It was the flux. Do you remember what the flux I'm talking about? I worked on that one.
Flux.
Told you I got to pull them all out. This one. No, nothing. Not even a little bit. That was funny. Come on. I worked all day on that stuff. I was like, people taking Calc 1 finals, whatever. I'm working on what the flux you're talking about. Okay. Anyway, this was called a flux integral, and what it's talking about is the rate that the fluid or the flow is going across a surface. That's what this is talking about. That's a surface integral of a vector field. It's called a flux integral. Now that you understand that concept, this is what it is. This is how we do it. What it is flux. Now, here's the whole point about where we're going for the last two theorems you're going to get out of this class. What the flux integral, man, I just laugh every time I say that. What the flux integral does, it is a surface integral of a vector field. But it kind of depends on what that surface is and how we can define that surface. Here's the main question that leads us to the next theorem. What if that surface, it has a very special case. What if that surface is not just any random surface, but it's a simple, closed surface? Does that phrasing ring a bell to you at all? Remember simple closed curves? And if we had them, we had Green's theorem, and it made our work a lot easier. Do you remember that? What if our surface is a simple closed surface? Means that it's this thing that if you filled it like a balloon, you filled it full of air or something or water, it would hold it all inside, okay? So there's no openings to it. It's simple. It doesn't intersect itself in any way. What if our surface is a simple closed surface? So let me make the case for it here real quick. We've already got surface integrals of vector fields. We know how to do them. They're called a flux integral. But just like before, if we have simple closed surfaces, like simple closed curves, we can make this easier. Green's theorem made things easier, not harder. This next theorem is going to make things easier, not harder. So, do you guys get the idea of where we're going on this? We have these things that are called surface integrals. They represent the flux. And if we got the surface that's a simple closed surface, we can apply this thing called the divergence theorem. You know, what in the world is that? Where's that coming from? You'll see it in the formula. The name for the divergence theorem comes for how we calculate it. Not because of anything up here right now, but because of how we calculate it. Here's what the divergence theorem says. It's still a way to do surface integrals of vector fields. It's still going to calculate the flux for us. So is this still going to be a flux integral? Yes, it's still going to be a surface integral of a vector field. It's just that if we have a simple closed surface, it makes these things easier. Here's how it does it. It says if you want to calculate the flux, which is normally this, if we have a simple closed surface, we can change it. Instead of thinking about this as a double integral over the surface, we can think about it as the triple integral over the... Do you remember using that? These things were surfaces, 3D surfaces. Do you remember that? If this surface is a simple closed surface, I can redefine it in terms of a surface for a triple integral. It says, well, what else is going to be up here? Take the divergence of your vector field. Hey, do you guys remember how to find divergence of your vector field? Yes, no, yes. Remember how to do that? It was a really easy thing. In fact, it was a dot product. It was a dot product of an operator, this thing called del, dot your vector field. Is this ringing a bell for anybody? Yes. Okay, a lot of head nods, that's good. dv. Just like before, with all of these theorems, with all these formulas, our main goal is to change, make sure it's satisfied, man. You got to make sure the divergence theorem is satisfied. What's going to satisfy that divergence theorem? Tell me right now, what's going to satisfy the divergence theorem? What type of surface am I looking for? If I don't have that, does this work? So you got to satisfy that. So firstly, I want to be finding the flux, because this thing still finds the flux. Does that make sense? So the wording up there says, I want a surface integral of a vector field. I want to find the flux, in other words. And then we got to verify that the surface we're dealing with is actually a simple, closed surface. Head, now that you're with me on that one. If it is, then satisfy divergence theorem, write this form, and then look at what your surface is. Remember, we never skip this step, like ever. So in our example, we're going to find the divergence of f, we're going to put it in there, then we're going to start looking at that surface. Head nod if you're with me on that one. That's it. That's all divergence theorem says. Is it hard? No. You do got to remember what divergence is. So if you're drawing a blank, you're like, oh my gosh, I don't remember. The divergence of a vector field is this. It's del dot f. Del was this idea of the partial derivative with respect to x, then y, then z added up. Does that make sense to you? And then f is this PQR. So if you really just wanted a formula for it, like, it doesn't make sense to me. It says take the partial derivative with respect to x. Of what? Well, of the p first. Then take the partial derivative with respect to y. Of what? Well, the next thing, the q. Because it's a dot product, it matches up the components of a vector. And then the partial derivative with respect to z of what? Well, r. That is what divergence it always is for a vector field. Is it hard to find? Yeah, it's pretty super easy to find. As long as you know partial derivatives and you can match up x with x's, y's with y's, z. There's no switcheroos here. It's partial derivative with respect to x of the x component, y with the y component, z with the z component. Show of hands feel all right with that one. Now, let's go over here and look at it. Firstly, tell me something. What's flux? What's it coming from? It's it's the rate of, that's what it means. What gives it to us? What gives us the flux? What are we doing in this whole idea here? What are we doing? What's that? I know it's integral. What type of integral? Yeah, there's like those little symbols like all over the place. We're dealing with integrals. What type of? Come on, folks. What type of integral?
Surface integral.
Don't lose it now. We've had 33 days of this. Okay, this is the final day. Don't lose it now. I got all of you here. I want to make sure it sticks because it puts a lot of stuff together for you. Okay, I don't want you to leave this class not understanding some of the connections I want you to make in the next 30 minutes. So, firstly, what gives us the flux? Some of you guys were saying it kind of. What gives us the flux?
Surface.
A surface integral of what? Through what? What things are we dealing with here? So it's a surface integral of a vector field. That's what's giving us flux. Does that make sense to you? That's what this stuff is. How can we calculate it? One way, just like that. If we can define z as a function, or the surface as z equals a function of x and y, we can do it just like that. We've already done that. If we have a simple closed surface, things get even easier. You go, triple integrals are easier? They can be. Let's take this example out. Firstly, tell me again, what's the flux? Well, what's it talking about here to you? Read it in English. It says flux means I'm finding a, come on people, surface integral of a... That's fantastic, and it's going to give us the rate of flow across that surface. That's what's happening here, okay? What surface? Does it give you a surface up here?
Yes. Yeah.
It has to. Does it give you a vector field that you're working with?
Yes.
It has to. Now, here's how we determine whether divergence theorem works. You got to look at the surface first and say, okay, what is the surface? What is that surface? It's a sphere. With a radius of what? Hey, are spheres simple closed surfaces?
Yes.
Will divergence theorem apply?
Yes.
Here's why. You got to get this. It's a surface integral of a vector field where your surface is a simple closed surface. That's what divergence theorem says to us. Does that make sense? So you check the application first. It's not just a surface integral. It's a surface integral of a vector field. And the surface is a simple closed surface. Those things have to be met for us to use this stuff. You don't just arbitrarily throw triple integrals in there, okay? This has some qualifications, and we meet both of them here. Flux, yes, that is a surface integral of a vector field, and we got a simple closed surface. With me. It's a sphere, okay, sphere. That's simple closed, it means it's going to apply. Here's how it works. Literally, all I want you to do right now, calculate the divergence. Our main goal is getting the setup right. Don't even worry. Don't even worry about the t right now. Don't even worry about that 3D region. Don't even worry about it. Just use divergence theorem. Can you please try that right now? It's good practice for your final, all right? Try to find the divergence of f, please. Did you find it? Was it hard?
No.
Kind of looks like it's going to be hard, right? Like, oh man, that sucks. It's not really hard. Well, let's look at it. The divergence of f says don't do this. Okay, this is from f, the vector field. Go take the partial derivative of, and you know what? You might want to label this just in case, you know, these things get mixed up or whatever. Or if you can't use divergence theorem, you have to know what p, q, and r are. Maybe p, q, and r. Take the partial derivative of p with respect to, seems pretty straightforward, partial derivative of the x component with respect to x, that's not bad, it's just, what? 1. Not I. What divergence does, do you see any eyes up here? If you're dot producting things, you can't even get a vector. Dot product just gives a scalar. This is scalar. At most, a scalar function. Does that make sense? At most, you have x's, y's, and z's. No i's, no j's, no k's. I know that you understand that. Dot products are really important you understand. So, partial of this, just this, that's the p. This doesn't involve the p. The p is the thing in front of the I. So, partial derivative of this with respect to x is 1. Partial derivative of q with respect to y is?
2.
J?
3. Wait, oh no.
J?
No.
And
3.
equals
6.
Wait a minute, that's it?
That's all.
Yeah, that's it. I told you this stuff doesn't get harder. The theorems people create aren't intended to make your lives harder. They're intended to do one of two things. Either make the hard stuff possible, not necessarily easy, bless you, but maybe possible, and make the hard stuff that is possible easier. Does that make sense? It's designed to make it easier. So here we go, okay, well, let's set it up. Then the flux, which is normally defined as a surface integral of a vector field over that surface, says because we have a simple closed surface, this is now a triple integral by the divergence theorem over the surface that's given to us of the divergence of f dv. Just like that. Now look what it does. It literally takes you back an entire chapter. Do you guys see that? These theorems take you back to old stuff, which we've conquered already. Now you tell me something. If I give you this, and I tell you what surface you have, this simple closed surface, can you do something with that triple integral? Do you understand why we don't skip this step? We don't skip the step because we want to have this down and then start thinking about what region we're working with, okay? Now we go, well, hey, what's the region?
Sphere.
Sphere. Sphere. For regions, 3D regions that are spherical or conical in nature, use spherical coordinates. For those 3D regions that are cylindrical in nature, or conical sometimes, use cylindrical. And for stuff that's planar in nature, use rectangular. That's why we learn all that different stuff in chapter 14, so that we can apply it here and have an easy time with it. It makes our lives easier. Takes us back to chapter 14, you go, okay, well, hey, let's use spherical. Let's use spherical. Tell me a couple things about this. Do you remember how spherical is defined? Rho. Okay, rho squared is what? Okay, so if rho squared is x squared plus y squared plus z squared, then from right here, rho squared is 4 and rho is 2. Rho always has to be positive. Does that make sense to you? Now, if you remember this, the way that spherical works, you always do what first? We always do rho simple first, then we do that phi, and then we do the theta. Is that ringing a bell to you? I'm going to walk you through because it's been a while, but that's got to ring a bell. So, firstly, we're going to do rho simple. Now, it should be pretty easy here. I mean, our rho, it's just a ball, guys. Our rho is going to go from what to what? It will be 0 to 2, but if you don't remember that, or if it's hard for you to figure this out, I told you to do something. I said for rho simple and for phi simple, it's two birds with one stone. Set x equal to 0, and you'll get both. So if I set x equal to 0, what we end up getting, x equal to 0 gives us this. That's just a circle. That's the trace on the YZ plane. Is this making sense to you? And it says, okay, it looks like this. 2 to 2. The rho is the thing that goes from the origin through the region and hits the outside of that ball. So the rho for sure is going from 0 to 2. Hey, now that you're with me on that one. But this also gives us our phi. Now, if you notice something, I haven't drawn the left side of this circle. I do that on purpose because our phi can never, ever, ever go past what value?
Pi over 2.
Pi over 2, that's right. So this gives us two things. It gives us rho symbol, then it tells us that our phi, I'm sorry, what did you say? Did you say pi over 2? It should be pi, not pi over 2.
Yeah.
I said, yeah, you're right. But I was just thinking I trusted you. That won't happen again. No, I didn't hear anybody. I was sure pi over 2. I'm like, yeah, that sounds good, man. Last lesson. Let's get the flux out of here. Anyway, see, now you're laughing. Yeah, I woke you up. Okay. Look, your phi, it starts here, and it goes this way. So your phi starts at 0, and it drops down this way. It can't go past. Otherwise, you'd be able to get there shorter this way. Make sense? So it goes from 0 to pi. Not 2 pi, but pi. Make sense? Now, if you wanted to figure out what the theta is always on the xy plane, always. Set z equal to 0. And I know this is all recap, we did it a while back, but it helps us out with a little review right now. If we set z equal to 0, we get x, we get y, but look, it's a sphere, guys. The traces all have to be the same. If it's centered at the origin, they're all gotta be the same. So it's just gonna be a radius of 2 again. Tell me something about theta. Does theta go all the way around or not?
Yes.
Okay, so phi's the only weird one. It goes just from 0 to, at most, pi. Okay, I'm going to stop here real quick. I'm going to do a little recap just to make sure that you guys are with me. Firstly, we're doing a flux integral. That's a surface integral of a vector field over a surface. And you go, okay, or of a surface. And then you go, fantastic. What's the surface? Oh, it's a simple closed surface. Divergence theorem applies. Find the divergence of the vector field. It's typically really easy. Partial derivatives, like normal. Put it right here as the argument of your triple integral. And then define your surface, your 3D surface, like you normally would. If it's a sphere, you're spherical. Our rho's 2, 0 to 2. If it's a full ball, we're going 0 to pi for phi, we're going 0 to 2 pi for theta. Should fence for with that one. Can you please set that up appropriately? Set up our triple integral. Okay. And then we're going to work it through. By the way, if you're wondering, just out of curiosity, why we don't use this for this example, when we start defining this in terms of z, we get that square root, the plus and minus. We basically eliminate half of our sphere if we choose one. Does that make sense? We'd be eliminating stuff. So it's easier for us for simple closed surfaces, oftentimes to use divergence theorem so we don't have to start redefining our surfaces. That's kind of a nice idea. Where you see the next one too. Probably could do it another way. But it's nice if we don't have to. It's nice if we don't have to start redefining how our surfaces look. Does that make sense to you? Yes, no? Okay. Did you set it up? Let's start doing it. I'm going to do it over here. Are there any questions on this, the divergence theorem from flux integrals? Do you see where it comes from? Do you see that it's doing the same thing, it's just over a very specific type of surface? Yes, no?
Yes.
Okay, cool. Just like Green's theorem. Green's theorem was a specific thing of a very... the same thing as a line integral. I put that just over a very specific setting where we had a simple closed curve. Okay, tell me. Come on, you only get like 2 more times to show me that you know this stuff. Tell me how that thing turns into a proper triple integral. What's it look like?
The triple integral.
Yeah, okay, yes. There we go. Triple integral.
6 rho squared sine phi.
6. I like the 6. Wait, I'm sorry. What's the next thing you put up there?
Rho squared sine phi.
Why'd you put rho squared sine phi?
The Jacobian tool? Yeah.
Love how you said Jacobian. Yeah, that's Jacobian. It's the way we transform dv, something that's just a three-dimensional volume of that region, into spherical. So it's got to be there every single time we do that.
dv. d theta. 0 to 2. 0 to pi. 0 to pi.
Beautiful. Did you start working it through? I want to see you work this one through. Let's practice this. We haven't got a ton of practice with spherical in a while. Let's work it through together. What's the first thing that you would do?
Integrate the electric rho.
So when we get the rho, we'd have that rho cubed over 3, yeah? 3 with the 6 is going to give you a 2. And then our rho is going from 0 to 2. From 0 to 2. If you plug that in, yeah, I plug in the rho, that's going to give me 8, this is going to give me 0, so I basically just have 8 times 2, I'm going to have 16 there. Did you guys get the 16? Sweet. Next up, let's do that one. Real quick, integral of 16 sine phi d phi. What's that?
Negative.
Negative. Did you catch a negative? It's a big deal. Man, it sucks to get all the way down here and do something silly, right? It's like, oh yeah, it's cosine, yay! Oh, the derivative, yeah. So then it goes backwards. So here we have negative 16 cosine phi, and then we're going to evaluate that from phi equals 0 to phi equals pi d theta. Hey, what happens? What happens when you plug in cosine of pi? But then with 0, you don't have to plug that in, right? Or do you?
You do.
Why do you?
It'll be 1.
Okay. So I got the negative 16. I've got cosine of pi is negative 1 minus cosine of 0 is 1. If we don't let our sign screw us up, that's 32. Negative 2, 16, 32. That means that we're going to get, if you look at it, we have this 32 theta. And we're just going to evaluate that from 0 to 2 pi. How much is our final answer?
64 pi.
The flux across the ball of that vector field is 32 pi cubic units per unit of time. That's the idea here. That's what's happening. Show of hands feel all right with that one. Tell you what I'd like to do. I want to try one more. I'm going to have you do most of this stuff, and then we're going to do with the last theorem, the last example. Just got the chills a little bit. Kind of cool. You're not as excited as you should be. This is freaking awesome, all right? Goodness. Any questions? So we're going to start here and work that way. Is it making sense?
Yeah.
Okay. Okay, come on, I asked you to kind of put all this stuff together, so I want you to answer the question this time. I'm asking you for the flux. What's that mean? What gives us the flux? What's that mean? Surface integral
Of the vector.
of the vector field. Very good. Do we have a vector field?
Yes.
We have a surface.
Yes.
Surface integral of that vector field for that surface gives us the flux. So I know that this integral, because of what we talked about, the flux, is a surface integral of that vector field over that surface, or across that surface. That's what's happening. Now, we're going to try to make it easier, because this thing doesn't have to be real nice for us. So there's two thoughts. Either we have a non-simple closed surface in which we cannot use divergence theorem, and we have to go back to the old stuff. Oh, we do have a simple closed surface, and we can use the divergence theorem. So number one thing, recognize what you're doing, man. If you're doing flux, you're doing a surface integral of the vector field over surface. Make sense to you? Then we start looking at the surface. Well, what's this look like? If I'm looking at the surface like that, this goes all the way back to chapter 11, your understanding of surfaces. Do you recognize that this has never left you the entire class? You've always gone back to how you think about graphs. Crazy, right? Told you it was important. Sometimes it doesn't sink in until, oh my gosh. Like every chapter, we have done the same exact thing. Dealt with these surfaces. What is that? Cylinder along what axis? What's this?
A plane.
It's XY plane. What's that one?
The XY plane.
So this is a cylinder with a top and a bottom. Just a basic cylinder. It's soda can. Yeah, it's like soda can with a top and a bottom. Does that make sense to you? Is it? Now how about this one? If this is a surface integral of a vector field, does divergence theorem apply for us?
Yes.
Is it a simple, closed surface?
Yes.
It doesn't intersect itself weirdly, basically cross like a curve would cross. It doesn't do that. It's closed. So if you had a soda can, nothing's coming out of the soda can, right? It's a closed thing. That's what this thing is. So divergence theorem does apply, and what I want to do right now is show that divergence theorem does apply, and then we focus on setting it up. Right now, I want you to do the complete setup, please. So as you're working, I'm going to be talking. So when we do this, we recognize the surface integral of a vector field. We look at the surface first. If it's a simple closed surface, this is typically the easiest way to do it. Divergence theorem makes it easier. You set up a triple integral where your 3D region is the surface. And that's nice because we know how to define that really easily. Divergence of f, that's easy to do, guys. That's partial derivatives. And then, once we translate it by divergence theorem, then we start looking at the region. Not before that. Not before that. Have you made it through the divergence of f yet? I always write off to the side and make sure that I get this thing right, because it's irrelevant if you know what you're doing after that if you don't get that right. I'd probably label this P, Q, and R. I want to take the partial derivative of P with respect to what? So that gives us I or not. Dot products don't give I's. Plus. Perfect. That's great. That's all you gotta do. That literally becomes your integrand. What's right inside the argument of your triple integral. So let's translate it. So I know that our triple integral, I'm not even worried about the region right now. I'm just going to write this. I'm going to write this here. I'm going to leave it dv, and then I'm going to start looking at the surface. Now, hopefully you recognize I'm doing this on purpose. I'm giving you a lot of the old concepts to refresh your memory for your final. That way we're getting some review in right now, and you're also seeing, oh, spherical still applies. Is it a big surprise we're going to use cylindrical with a freaking cylinder? This is why it's nice. Because if you use divergence theorem and you change the surface into a triple integral where it lets you easily deal with the surface, and you got things like spheres, you get spherical. Things like cylinders, hey, we can use cylindrical coordinates for triple integrals. It makes it just very, very straightforward, very, very nice. Are you seeing the point of doing this right now? So let's look at that. So this is obviously a cylinder, which means that we've got a 3D region that's a cylinder. We're going to be using cylindrical. Now you might have to dig down a little bit on this one. With cylindrical, with spherical we did row simple first every single time. With cylindrical, do you remember what we do first every single time?
Z simple.
We have to do Z simple. Is that convenient for us?
Yes.
With cylinders along the Z-axis? Yeah, you better believe it. That's awesome. So if we do Z simple, literally all we're looking for is, hey, what two functions can we mash Z between? Well, that didn't have any Z's in it. That's 0, that's 5. It's literally right there in front of you. Again, that's why this makes it nicer. Not harder, not worse, nicer. Okay, next thing. Come on, next thing. What's the next thing?
The XY.
Before that. So I did Z simple, and what I'm trying to do is set up my triple integral. So cylindrical does Z simple first, and then it deals with two other things. It deals with R, and it deals with... Okay, so we look at our region. If we're doing cylindrical, and we did Z simple first, our region is on the what plane? Okay. So that means that I'm going to write out the same way every time to keep consistency. R is on the XY plane. So let's graph that. Look for everything that has X's and Y's and put it on that plane. In our case, it comes pretty nice. We have a circle with a radius of 2 centered at the origin. And then we go, hey, cylindricals basically just take care of the Z and you got polar. It's the same stuff. So when we start defining x squared plus y squared equals r squared, well, that means that r squared equals 4 or r equals 2. And now we get two things. We have to mash r between two functions of theta, and then theta between two constant angles. That's what we got to do. What's the r between? Between where and where? We had so much work on this. So the r goes through our region on the xy plane from 0 to 2. The theta goes
0 to 2.
all the way around. That's it. We're going to do two things right now. The first thing we're going to do is just like we normally did, set up the triple integral, set up the bounds of integration, set up the d whatever's over here. Make sure you understand that we are in cylindrical right now, and we just changed to polar. That matters. Okay, the way I taught you was that way. I said we do z, and then we have polar. So you're going to have something special up there, just like we had the d phi. Well, we're going to erase it. The rho squared sine phi d rho d theta, whatever that was. We're going to have some special stuff here. So I want you to set up right now the bounds of integration and change this piece, please. We'll worry about this in a minute. With cylindrical, what goes first on the most inside integral? From where to where?
0 to 5.
Beautiful. What's next?
1.
0 to 2, 0 to 5.
And lastly?
0 to 5.
Fantastic. That's exactly right. That's exactly how your bounds of integration should look. Show of hands if you got it. Is it way easier now than like the first time we did it? Crazy how that works, huh? Now, the d, that's got to change. Come on, folks. Let's get this right. You got to match up your variables with the d of that variable. And we also have something up there. What's this going to be over here? Where's the r coming from? The r's coming, Jacobian, but r's coming from polar. When we did the polar here, that's what given that r dr d theta. We just put the r in front of the dz so we don't lose it. You don't have to do that. But we have a r dz dr. Shoot. We have an r dz dr d theta. R dr d theta is just the polar. That's what's happening. The cylindrical works z first, then polar. That's about it. I don't know if you're okay with that one. Now, As soon as we determine divergence theorem works, we find divergence, we put it here, we deal with the 3D region, that 3D simple closed surface, we identify it for a triple integral, and then we change these pieces. But you have to keep in mind that these pieces only change to match these variables. As long as you're matching those variables, you're good to go. So, here's the question for you. Do you change the z here?
No.
It's real common for people who don't know what they're doing. Go, oh, that's rho squared. Yeah, I'm done. Would that be a good idea?
No.
Do you have any rows?
No.
That shape, that's not spherical. Spherical don't work real well with cylindrical. Cylindrical works real well with cylinders. Do I have to change the z at all?
No.
Should I change the z?
No.
No. In fact, that's the first variable that you're going to have to integrate with respect to, so don't change it. Do I have to change the x?
Yes.
Do I have to change the y?
Yes.
So change them both at the same time. What's that become? By the polar definition that you just put right here. That's why we put that stuff on paper, not just do it in our head. You already have that. You change this to r squared for your region, therefore you have to change it to r squared for your integrand. What's inside of there? You got to do that. So this becomes r squared plus z squared, and then we have that times r. Just keep in mind, you have to have parentheses around that. Here's your r squared, here's plus z squared, and you're multiplying the whole thing by r. Does that make sense to you? I want you to start working with it. What's the first thing that you would do right now? Yeah, you distribute before you integrate here. So distribute the r. You technically don't have to. You could hold that out till later, and then distribute the r later. It doesn't really matter. It's a constant with respect to z. I like to not lose it, so I like to distribute that one. So I want distribution here. I want you working through the dz, plug in some numbers, and let's see where you're at, okay? So distributed, making sure that that's right, don't want to screw that up. Then dz first. I said it. Did wrong. Z, add one, divide by that one. Did you make it that far? Sweet. Basic integral. What do we do now? Plug in for what variable? Very good. That's why we typically write this stuff down, so we know what variable we're working with at that time. Integrate with respect to z, you're plugging in for z's. Man, it's getting nasty. You got a calculator with a fraction button on it, I hope? You're going to need it. (5r cubed plus 125 over 3r). If I've done my math right. Did you get the same thing I got?
Yes.
All right. Now what? Yeah. So when we integrate with respect to r, we're going to get this 0 to pi, sure. 5/4 r to the 4th. And then 125 over 6 r squared. And then we're going to evaluate that from r equals 0 to 2. and then do our last integral, hopefully get the right answer. $250/3. Gotta check my work on that one. Are we okay on that too?
Yeah.
I'd probably combine those before you went any further. Get 310/3. It's 20, 40, 60. 310/3. Makes it just a little nice. You don't have to evaluate twice. You just have to evaluate one time. Does that make sense to you guys? Now if we evaluate that from 0 to 2 pi, looks like 620 pi/3. Nice number, right? Cool stuff. Did you get the same answer?
Yeah.
That's great. That's all I'm looking for, is that you understand when divergence theorem works and how it makes our lives nicer to deal with this stuff. Does your fans feel okay with that one? Candace, question? Do you understand what divergence theorem does? Do you understand that it works with the same stuff that surface integrals of vector fields work with? It's the same thing, just a nicer way to deal with it. Are you ready for the last theorem? We're going to do it right now. I want to ask this question. It's going to lead us to this. What is that? Very good. That's a line integral, not a surface integral, single integral. Line integral of a vector field. A curve through a vector field. Do you remember doing that stuff? Does this make any statements about the type of curve that we have?
No.
We've done this. We beat this to death in the first part of chapter 15. We did a ton of line integrals. It finally led us onto Green's theorem. Do you remember what Green's theorem dealt with?
Simple closed curves.
Simple closed curves through non-conservative vector fields where the simple closed curve was on a plane. Yes, on a plane. Green's theorem dealt with that, where the simple closed curve was on a plane. We still had a vector field. We were still doing what? What does this do? What does a line integral of a vector field actually calculate? What's it do for us? Yeah, it does work. So this calculates the work done by moving a particle through a vector field on that curve, on that simple closed curve. Head down if you're okay with that one. Tell me something. What if the vector field is conservative? How much would that be every time?
0.
Very good. If it's non-conservative, we have Green's theorem. If the curve is on the plane, do you guys get it? If it's on the plane. The question is, if this is still work done, which it is, if it's still work done, do you guys get that? This is a line integral, simple closed curve, that's what that means. Through that vector field says we're doing work. What if the curve is no longer on a plane? Does Green's theorem apply if the curve is not on a plane? Yeah. If you look back at Green's theorem only had two partial derivatives. Do you remember that? It said partial derivative of q with respect to x and p with respect to y. It didn't have a z with it. What's going to let us deal with line integrals? Back to line integrals again. Of the simple closed curves of a vector field, well, there's a generalization for Green's theorem. It's called Stokes' theorem. So what I want you to think of this as is like taking Green's theorem and just making it general, where your curve, your simple closed curve, does not have to be bound on a plane. Does that make sense? It doesn't have to be on a plane. So when you think about Stokes' theorem, it's real similar to Green's theorem. It's just that it can be in 3D rather than on a plane. Head nod if you're okay with that one. What lets us deal with this? What lets us deal with this is Stokes' theorem. What Stokes' theorem says. Something kind of cool. You're like, wait, line integrals, why did we make this major shift? Why are we talking back? Weren't we just talking about surface integrals like 5 seconds ago? Yeah. But look what Stokes' theorem says. Again, Stokes' theorem, a generalization of Green's theorem. It says that, hey, Green's theorem said your simple closed curve was on a plane. Stokes' theorem says, what if it's not? Well, then we can use something that's a little more 3D to deal with it. It says we can find the line integral of a vector field, still do work through by moving a particle along that simple closed curve, through a vector field. But if that curve is not on a plane, Stokes' theorem says that the work done by moving a particle along that simple closed curve through that vector field is mathematically equivalent to the surface integral. Look at that surface integral, you see that? Of the curl of the vector field ds. There you go. It's kind of crazy. It's making this analogy between, well, a single integral and double integral. Do you remember how Green's theorem did that? It did the same thing. It took a line integral, simple closed curve on a plane, and said, hey, what about the region that simple closed curve contains? And it made a double integral out of a single integral. And this is doing the same thing, but it's doing it in 3D. And now there's just similarity between that. That's what I want you to see, that this is very, very similar. Well, if you want to write down the statement, here's a couple statements. For Green's theorem, C's on a plane. For Stokes' theorem, it's not. If it were, we'd have Green's theorem and we would be done. Second, what this says in English, it says the work done along C through F equals the flux. Verify that for me, that this is still flux, yes or no? Surface integral, a vector field. Oh, wait, crap, goodness. Curl F. Does curl F still give you a vector field? We're going to deal with that. It does, yes. So we're going to deal with that in a second. So, it says this. It says that work done on C work done along our simple closed curve C through the vector field F equals the flux of the curl of our vector field across what? Let's unpack this for just a minute before we do our very last example, and then we'll be good to go. Let's unpack this for a second. Do you guys understand the idea that we're back to line integrals and still calculating work through a vector field along a simple closed curve, just is not on a plane anymore, it's 3D. It says, well, what is it equal? It's equal to a surface integral of a vector field. Is that a vector field? Yes, it certainly is. I'm going to show you how to deal with that in a second. This is the flux. Surface integrals of vector fields is the flux. It says that the work done on that line integral is equal to the flux of the curl of F. Oh, but wait a minute. Over what? What over what? What is that thing?
Surface.
What surface? What surface? I don't have a surface. I've got this curve. I've got this curve. Is that curve connected? Is that curve a simple closed curve that makes like a loop? Is that curve a simple closed curve that makes like a loop?
Yeah.
Okay. Like Green's theorem, remember that? Do you remember how Green's theorem, you remember how Green's theorem dealt with the region that curve encompassed? Do you remember that? This deals with the surface that simple closed curve bounds. Not only that, it deals with any surface where this curve is the boundary. Stokes' theorem is very impressive. Do you remember that whole independence of path thing? Where you're like, hey, you can go along any curve, it gives you the same work done. Do you remember that? Through conservative vector fields? This is similar. It's not the same thing, but it's similar. It says that as long as this curve is a simple closed curve in 3D, you can do a flux integral, a surface integral of a vector field for any surface that has that curve as its boundary, and it will calculate the correct flux for you. So this says that the work done along C through F equals the flux surface integral of the curl of F. It's still a vector field across any surface where C is the boundary of that surface. That's freaking cool. Does that mean we need a surface? Yes. Does it mean that any surface will do? Yeah. As long as C is the boundary, that's what's important. Now, I made a statement a while back. I said that, like maybe 5 minutes ago as we were going through it, I said, wait a minute, if that's a flux integral and that's a vector field, then it's old stuff. It is old stuff. Here's the idea. Now, it's a beautiful idea. It says, well, wait a second. If we do the curl of F, verify that the curl of F comes from our vector field and still gives you a vector. Remember that curl F still gives you a vector, has i's, j's, and k's? Then if we do just a little mathematical maneuver, treat curl F as a vector field. Then this thing if I treat that as this new sort of vector field, I'm going to put these little quotations around so you see it's a different F. Okay, it's a new F. I know I'm using the same letter, but it's a new F. Well, that looks pretty darn familiar, doesn't it? In fact, that's exactly what we had the last, I don't know, hour and a half of this lesson. Tell me 2 ways that we can deal with this right now. What if S is a simple closed surface? What could I do right now? Divergence theorem could apply to this. If you have S being a simple closed surface, if you can define it like that, then we have a simple closed surface. You could use divergence theorem. What if it's not? Could we do it? Yes, that was right before that when we did flux integrals in general. We said, well, this could also be, so this could be divergence theorem if S is a simple closed surface. This gets a little tricky though. Because this F, where you'd find the divergence, is not that F. It's the curl of that F. Does that make sense? So you do the curl, then divergence, if you have that simple closed surface. Simple closed surface. Or we go back to this. Let's suppose that S is not a simple closed surface, which in general it's not. It's just something where, and it'd be very unique to have this, because can you really talk about a curve being a boundary of a simple closed surface? Does it really have a boundary? It'd be very unique if we had that. Generally, it doesn't happen. I'm just saying in generalities that you make connections here. Okay, the connections are, we are getting a surface integral out of a line integral. That's pretty impressive. How do we deal with them? One way we deal with surface integrals is divergence theorem. That's one way. But if it's a simple closed surface, then C boundary kind of falls apart a little bit. So in general, we deal with this. This was the other way that we dealt with surface integrals of vector fields, flux integrals. But this also means that, hey, how about this? Can you figure this out? This is implying that our surface is defined in a certain way. How is our surface defined? Not vectors, or not for parametric surfaces. I want you to look at the partial derivatives. What are the partial derivatives with respect to? So this would be a surface defined as z equals... Perfect. Yeah, that's exactly right. Just like it was before. This is what happens every time. This doesn't really happen with Stokes theorem, at least not very often. This happens every time. I'm not even sure if that can happen, but this happens every time. Shall we try one? One. Seriously, one. I have no more written down. It's the last piece of paper. It's almost sad. It's going to make me cry. Not really. Going to Costa Rica, man. Woo! See y'all there. I'm building a house. Building a house for 12 hours a day. But it'll be fun. What was that question back there?
I just said that was the last example you had that book, huh?
Sick. Wow. Right there. Out of 750 pages of notes and done homework, we end up the last one.
And you actually went through your guide and sat down for this, and prepared for this class, and write that out? And just, I mean, that's part of what, when you do as a professor.
I spent three months, 8 to 10 hours a day creating this class. I gained 15 pounds. All I did was calculus and eat cookies, man. I gained 15 pounds. I'm just finally losing the last 5 right now. Someone online was like, man, Leonard lost a lot of muscle and gained some fat. Something must have happened to him. Must have had a kid. Well, yeah, I did. Well, I didn't have a kid. I'd look good if I had a kid. But yeah, I did calculus. That was my baby that I produced. All right, here it is. I'm delivering it to you right now. It's kind of gross if you think about it. You know I'm going to milk this for all it's worth, though, right? We're gonna go Leonard speed on this one. You're gonna understand everything about it before I let us be done with this stuff. So let's find the line integral of this vector field. I've given you a vector field. What else do I have to give you? Curve. Got to give you one curve. Yeah, you know what, that would work if we had 2 surfaces coming together that created a boundary that created that. That'd be fine. If you could define them as the boundary of 2 surfaces. There we go. Of course, what I've been preaching the whole time is that you get the setup correct and understand the fundamentals of what's going on here. So let's read the first part. What am I even asking you for? A line integral. Very good. Somebody else. A line integral of a vector field where we have a simple closed curve. What 2 theorems could possibly apply right now? Green's theorem could possibly apply if the curve happens to be on a plane. Very good. Is it on a plane? No. This is a plane and a... Do you see the cylinder? Here's a cylinder, here's a plane. It's not... The curve, while it could be looked at as flat, is not on a coordinate plane. We can't do it with Green's theorem. It does not apply. Does that make sense to you? What other theorem would apply?
Stokes.
As long as we have a simple closed curve. So you think about this. This is what I'm trying to get you to do with divergence theorem, with Stokes theorem. Look at the region. Look at the curve that's created. Now, I'm not talking about a 3D surface here. This is not what line integrals do. Line integrals talk about a curve through space. Well, let's look at it. The intersection of a plane through a cylinder. What's that give you? Gives you a curve. Gives you this curve that's cutting out the edge of that cylinder. Does that make sense? That's what's happening. It's not a surface. So a surface integral right off the bat doesn't apply. But a line integral does of a simple closed curve in 3 space. Now what Stokes' theorem says is, even though it's a line integral, I can use a surface integral of a vector field to do it. I can use a flux integral to do it. Does that make sense to you? So right now, write down Stokes' theorem. All Stokes' theorem says is that this thing can be calculated as this thing. That's all it says. Head nod if you see that Stokes' theorem applies and that is what it says. Head nod if you do. You see that. Okay, explain to me then. Why Stokes' theorem apply? Simple closed curve that's not on a plane
Through a non-conservative vector.
through a vector field. Non-conservative, I don't know. We can check it, I guess. But I guarantee it's non-conservative. Why? Why do I guarantee it's non-conservative right now? Why do I guarantee that vector field is non-conservative? Because the curl of f is 0. What? That generalizes something. It says that through any conservative vector field, line integral of a simple closed curve will be 0 every time, because Stokes' theorem says it will be right there. Does that make sense? It's pretty cool. Because the curl f is 0, get 0. Impressive. Now, do you remember how to find curl f? Because it's going to kind of depend on that, right? You're like, curl, who needs curl and divergence? We do. These theorems rely on them. If you cannot do that, you cannot do these theorems. And they're very important that we be able to do this to find work done through vector fields. Can you please calculate curl f for me right now? If you remember how to do it, it's that, like a determinant of that matrix that we create. We have I, J, K, we get the del, and then we cross it with P, Q, and R. So probably pretty useful to be able to identify P, Q, and R. Okay, that's on you guys. Go for it. I've done the setup for you. Hopefully you see where it comes from. Partial derivatives, that's your del. P, Q, R. Do the curl. Remember how to do it? Cover this, partial minus partial. So what's this give us? 2 minus. Partial of this makes it z, 0. Cool, love it. Minus sign, cover that up. Partial derivative is?
0.
Minus. Let's be careful about this one. Partial derivative of this with respect to z is a negative sign, and I'm subtracting it. Plus sine z. Which is going to change to a minus. That's why we write this stuff down. You know that sign errors are the biggest thing for us, right? Sign errors in algebra. Write this stuff down. Don't put too much in your head. Or we start making errors, and then nothing works out right for us. And that's a bad thing. Then the last one, we covered that up. Partial derivative here.
2x.
Minus. Did you get it? Simplify it a little bit. Ladies and gentlemen, are we okay with that so far, for real? Now what I'd like you to do, whenever you have to do this, right now, redefine this. You see, if this is a surface integral, then that has to be a vector field, and some of you guys didn't catch it before, but verify this. This is a function-defined vector field. It's giving you a vector at every single point, x, y, and z. This is a vector field. Redefine that as your vector field. So now our f, our new f, is that. Why? Why do we want to do that? Well, if we do that, then we can start labeling P, Q, and R. Then we can start doing, well, changing I'll write it this way. Changing this into this. Because if we have a vector field, and if we're finding the flux integral of that vector field, which is exactly what we're doing here, then we can start using this old stuff. By the way, we're not using divergence theorem because we do not have a simple closed surface. And I can't think of an example where we would have one. This one, well, let's look at the surface. Let's look at the surface. If we define the surface, what's happening is all I need, now be careful here, all I need is for some surface to have a boundary of this curve, this intersection. Are you listening carefully, please? Please listen carefully. All I need is any surface that has this curve, the intersection, as a boundary. Does that make sense? This can be used as that surface if we also look at this thing as the region that contains that as the projection. Because remember what this does. This says that D is the region as projected onto the xy plane where z is a function of x and y. Is this making sense to you? Say it one more time. The curve has to bound whatever surface you have up there. Doesn't matter what surface it is, doesn't matter. But it has to bound that surface, okay? So define some surface where that is a boundary, but then when you do that, the region that you get on the xy plane comes from these two things as well. That they have to be there. So let's define our function of x and y. Do you have something up there that's defined a surface in terms of z equals x and y? Do we have that? Yeah, what is it?
2 equals 2 minus x.
Can you right now go back to your vector field and identify P, Q, and R? Let's see if you know what you're doing. Identify P, Q, and R. Can you do that on your paper here real quick? Just try it. Try something. Put something down. Here's the question. Is this P, Q, and R right now? No. So there's a change to it. A lot of people get jacked up on that. They go, oh, you're using P, Q, and R. It's got to be that one. No, that's what we use to find the curl. And then we make this switcheroo and we say, hey, that curl of f, that becomes our new vector field so that we can even do this. This right here is my new P, my new Q, and my new R. If you want to do notation, it's horrible notation, but maybe this. Saying this is coming from that new vector field, my new P, my new Q, and my new R. Otherwise, you get to define new letters. It's up to you. I don't really care. That's my notation. So use whatever you want. But that's how I think about it, so I don't get confused between my new vector field and my old one, my new p's and my old p's. Does that make sense to you? So let's try this stuff. Let's go ahead. What's the two other things we got to do before we set up this double integral? What do we have to do? Yeah, partial derivative of what? The surface that sees the boundary of. So that's this surface. I want to find the partial derivative of, and if you want to write it as this so it looks a little nicer, that's fine. The main goal is take the partial derivative of that surface that you defined, z as a function of x and y. Take those partial derivatives. What's the partial derivative with respect to x, please? Come on, don't let me down now. What is it?
-1.
And the partial derivative with respect to y is?
0.
Okay. Can you take your new p, your new q, your new r, your partial derivatives of the surface that we just defined, z as a function of x and y, and put them in that double integral? Remember, we never look at the region until we set up the double integrals. That's kind of a universal thing we've been practicing the whole semester. So set that thing up right now. And tell me what I should get. Sorry, I kind of fell asleep there a little bit. I'm sorry. -2. I like the -2 because it says, hey, negative, and that's my 2. Head down with me on that one. Keep going. Times -1. Times -1. This multiplied with a negative in front. Make sense? Okay, nail it. Minus sign. Minus? Good, it would be negative sine z because it goes with the sign. No pun intended, I mean, literally goes with it. Times?
0.
Oh, 0. Love when that happens. Plus, no partial derivative, you just give me the r. Yeah. Man, we've done a lot on this problem. Line integral, not on a plane, Stokes theorem applies. Find the curl of your vector field, treat that as your new vector field, a new p, a new q, a new r. Take a surface that has this curve as its boundary, which we have here, defined in terms of x and y, take your partial derivatives and plug it into the flux integral formula that we created a long time ago. And now simplify it. Simplify it, and I'm really hoping that you remember what to do now. I'm really hoping you remember what that region means. What's that region? What plane is that region on? So it works the same way as everything else we've done. You look at the intersection, you say, hey, look at that intersection from the top, like that. What shape is it going to make on the xy plane? Well, if that's a cylinder along the z, and that plane's just cutting it, then that shape, that surface that curve encompasses through space, when you look at it from the top, that makes this projection of just the cylinder itself on the xy plane. And if you're like, man, I can't get that, draw them all. That's fine. But just recognize that if you draw the region on the xy plane, what's the value of z on the xy plane? Firstly, are you guys okay that the picture we're looking for, the region, is on the xy plane? We're basically making it z simple here, if you will. We're making the function z equals function x and y, which means the domain, the region there is going to be on the xy plane. That's what we're trying to do here. So if z equals 0, then 2 minus x equals 0, and x equals 2. Can you draw that on the xy plane? If we're on the xy plane, z is 0, man. So we got 2. Head nod if you're okay with that one. Let's look at the other thing that's basically creating our boundary here is this. Let's draw that too. What's that going to give you? Now, how many circles have we had in this class, huh? Radius of? Let me ask you a question. Is the line x equals 2 relevant to the region that's created on the xy plane, is it relevant? What if it would have cut through it? Would it be relevant?
Yes.
Yes, but if they don't intersect, why don't they intersect? We had an example like this a while back. We got this cylinder, right? And we got this plane that's cutting it. That plane intersects the cylinder right at the xy plane. Right at z equals 0. Hit another 0 key on that one. Okay, now, can you finish up the rest of this problem? Try it. What do you think you're going to do here for that region? Remember, D just means the region. What do you think you're going to do?
Convert it to polar.
Yeah, why would you convert it to polar?
Circle.
Beautiful, do it. How would you do it? Don't mumble at me, man. I can't hear you. I hear you mumbling at me. How would you do it?
Define R and bit.
Define R and bit. Okay. What two variables are going to give you? What two variables give you the circle here?
X and Y.
So those are two variables that you want to call R. Like this, yes?
Yes.
That means that x squared plus y squared in our case equals 4. So R equals 2. R squared equals 4. R equals 2. This is the circle. R equals 2. No big surprise. It's a circle with a radius of 2. Now, I also told you to do one more thing. Every time that you have to define something in terms of polar, that necessitates a change, a parameterization for your x and for your y. Write that down. Write that down. That way, if you have any extraneous x's and y's floating around in your integrand, you can change them, okay? So as soon as I do this, what's our x become?
R is
And that allows you to change it. So I want to see a proper setup, and then let's check that. I'll give you about 30 seconds to give you a proper setup. Remember, this is just a double integral right now. So all I need is two different variables. All I want is two variables. All I can have is two variables. And you're changing a dA, not a dV. So you're not doing like cylindrical, you're not doing spherical, you're just doing basic old polar. What that means is, with that circular region, we're doing polar. I know at the very end, I'm going to have a what? Beautiful. That means that I have to go R, then theta. I know that for this region that was projected from that surface onto the xy plane, my R goes from 0 to 2, sweet. And it's a full circle. So our theta is going from 0 to 2 pi. That's changed our bounds of integration, it's changed our dA to what we want, that RD theta because region polar. Now we look at the inside, the integrand. What's got to be in there? 2 can't change, plus. That's why we define that. So you know what to do with any x's and y's that are in there that aren't like x squared plus y squared. And you got to have parentheses. Did you make it that far? Mm-hmm. Good, you've learned a lot. That's fantastic. What's the next thing you do? Because we're going to work through this one. Do what now? Yeah, let's do that. You could also factor out the 2 if you really wanted to. I don't think I did that, but you certainly could do that. What now? Let's end with some good participation here. What would I get when I start integrating?
R squared.
And?
2/3 R cubed.
Okay, right-siders, we're plugging in for what variable, please?
R.
0.
Yes, for what variable?
R.
So if we do that, we got this, looks like 4/16. D theta. Plug in 0, you get 0. After that one, come on, stick with me. Middle people, how about you guys? What do I get when I integrate respect to theta?
4 theta. Plus 16 sine theta.
Plus, yeah. Is it going to matter?
No.
No, but... Say what now? Do we?
Yes.
It's good to me. Yeah, so plug in definitely plug that in, we're going to get 8 pi. Plug in 2 pi here, sine of 2 pi is 0, sine of 0 is also 0, theta with 0 is 0, we get 8 pi. Now you tell me what it means. Is this flux?
No.
Yes and no. It's the flux over that vector field, if you want to consider that, of that surface, that plane, that little disk. It's that, if you want to consider that. But what it came from is still on the board. What is it?
Work.
It's work done by moving a particle along the the intersection, the boundary of that surface and that one. So along that curve, through 3 space, through that vector field, and that is it.
I want to keep going.
Any comments or questions or anything about this concept? Do you feel like you understand the interplay between surface integrals of vector fields, divergence theorem, which helps you, and Stokes' theorem as just a generalization to Green's theorem?
Yes.
Then I think I've taught you everything. This pretty much ends all of your calculus. It's crazy, right? The end of calculus has been a long road. Go to Costa Rica.